Hi guys, welcome back to my channel. So how are you guys? I think you had a nice summer break. Did you enjoy your summer break, guys? Now we have to focus and please come back to the studies. Yeah, some they have summer break in the back home and some they have summer break here. Now we know that schools and colleges also started. Then please turn to the studies, turn to the work. It's a kind of work. Studies is a kind of work. So please focus on your studies. Now I'm going to teach you shape of the molecule. Let's start. Okay. Now see that it's a it's a kind of covalent bonding. In that we have the shape of the molecules. In the shape of the molecule, definitely you will get 3 to 5 marker, mostly 3 to 5 marker. And I'm sure uh, the way I'm going to teach the shape of the molecule, you can't find this type of explanation in any textbook. Let's start to go through the shape of the molecule. We have to go through the periodic table. Let's start with the periodic table, and I want to start with the group 4. Group 4, group 4 elements. Agree? Yep. Now see, group 4 elements. Group 4 we have carbon, silicon, and germanium, tin, Pb. Tin Sn, Sn and Pb, tin Pb. Let's see the group 4 elements. Sn, Pb. Now, if the central atom is from group 4 and having 4 bonded electron and no lone pair. Now let's see the shape. If the central atom is from group 4, if the central atom what is meant by the term central atom? Central atom is the only one atom and having many other monovalent or mostly halogens around it. So if the central atom is from group 4, having 4 bonded pair of electrons and no lone pair, no LP, no lone pair. If the central atom is from group 4, having 4 bonded pair of the electron and no lone pair, our central atom is from group 4. If the central atom is from group 4, having 4 bonded pair of the electron and no lone pair, the shape is always tetrahedral. Shape of the molecule, the shape of the molecule is TD, is tetrahedral, perfectly TD, tetrahedral. And a BA, what's BA? British Airways? No, BA is the bond angle, and a bond angle is always 109.5. So what's the condition? The first condition is if the central atom is from group 4, having 4 bonded pair of electron and no lone pair. Central atom, anyone, you can pick anyone. Carbon having 4 bonded pair of electron and no lone pair. Then the shape is tetrahedral, perfectly tetrahedral, and the bond angle is 109.5. Can you give me some more example by choosing central atom from group 4? Yeah, hydrogen or any halogen. Any halogen, you can take any halogen. You can take any halogen, fluorine, chlorine, bromine, iodine, you can take. So methane, CH4. Carbon is the central atom in CH4. Look at that. Carbon is the central atom Either you can take hydrogen or any halogen atom, like fluorine, tetrafluoromethane. What's the bond angle? 109.5. And what's the shape? TD. I can give you many examples, guys. Carbon, what's the bond angle and shape of SiH4? Like methane, this is called silane. Same thing, 109.5. TD, tetrahedral, tetrahedral. The short form for tetrahedral is TD. Can we take chlorine, CCl4, carbon tetrachloride? Yes. What's the Ba? What's the bond angle and what's the shape? Shape is tetrahedral. Bond angle is 109.5. Trichloromethane, tribromomethane, Br. Triiodomethane. All they have bond angle 109.5, perfectly tetrahedral, and each angle, this angle, this angle, this angle, that angle, all are 109.5. They are exactly at equidistance because there is no lone pair. I'm coming to the lone pair. So when we will get a tetrahedral geometry, the central atom is from the group 4, having 4 bonded pair of electron and no lone pair. These are the conditions. With the condition, central atom is from group 4, having 4 bonded pair of electron and no lone pair. You can give any example, guys. SnCl4. What's the bond angle and shape? Tetrahedral, and a bond angle 109.5. Why I was telling to you, we are going through the periodic table. So to learn the shape of the molecule, we have to learn and find out the central atom belongs to which period. That's the most important point, and that's concern. That will help to find out the shape of the molecule. We can't memorize, guys, because in the examination you will get any example based on TD shape. Now, after the group 4, I want to jump to the group 5 element. I want to move across the periodic table. Then I want to go to the group 5, and let's see. Group 5 elements. So central atom is from group 5. Now, group 5th element or group 5 element, same thing. Group 5 elements, you can write group 5, or in some periodic table I have seen 15th group. Why it is called 15th group? They included 10 group from the transition metal. Actually, it's group 5. Group 5 elements: nitrogen, phosphorus, arsenic, antimony, bismuth. I need this space. I'm sorry. Group 5. So group 5 elements: nitrogen, phosphorus, arsenic, antimony, bismuth. If the central atom is from group 5, having 3 bonded pair of electron with 1 lone pair. How many electrons are there in the valence shell of group 5 element? 5. That's why they are placed in group 5. So there are 5 electrons in the outermost shell. Out of 5, they form 3 covalent bonds with a 1 lone pair. So if the central atom is from group 5, if the central atom is from group 5, or group 5th, having 3 bonded pair of electrons and 1 LP and one lone pair. and one lone pair. Then what's the shape and what's the geometry? Sorry, geometry and shape is very similar. What's the shape and a bond angle? Let's see. What's the condition? If the central atom is from group 5, having 3 bonded pair of electron and a 1 lone pair, then the shape of the molecule, is, any idea? Then the shape of the molecule is trigonal pyramidal. Then the shape of the molecule is trigonal pyramidal. It is not a planar molecule, guys. This is a 3D molecule. Look, central atom is group 5, having 3 bonded pair of electron and 1 lone pair. Hydrogen, hydrogen, hydrogen. Look at that. It's like a tripod of the camera, guys. These two, look at this, is the white plane of the board. These two bond, which is wedge bond, coming towards you. Agree? And the dotted bond, it's towards me. That a dotted bond is just inside, goes inside the board, or it's away from the student. That's twos are coming to the student. There's 2 bonds. Look at that. These 2 bonds are towards you guys, and that's towards me. This is like a trigonal pyramidal molecule with a 1 lone pair. So what's the condition? The condition should be if the central atom is from group 5, having 3 bonded pair of electron and 1 lone pair. Okay, I can give you many examples. Now, what's the shape of the molecule? Trigonal pyramidal. And what's the bond angle? Bond angle, look at that. Bond angle we have seen just now for methane. The shape is TD, shape is tetrahedral, central atom is from carbon, and the bond angle is 109.5. When you move from group 4 to group 5, there's a presence of 1 lone pair. Due to the presence of 1 lone pair, the bond angle slightly decreases due to the repulsion between the bonded pair of electron and lone pair of the electron. So, presence of 1 lone pair, we can decrease the bond angle from 109.5 to minus 2.5. So, presence of 1 lone pair decrease the bond angle by 2.5. So, how much is the bond angle now? 107. Shape is trigonal pyramidal and it's a 3D molecule. Look at that. So 2 bond towards you, these 2, these are called the wedge bond. Sometimes they will ask to draw 3D shape, especially in case of the transition metal complex. These are towards you guys, and that's going into the board, into the white plane. Yeah. So 107. The bond angle is 107 due to the presence of 1 lone pair. I will give you one question. After finishing all the example, I can give you as many as example. Like look at that. Group 5, and how many elements? 1, 2, 3, 4, 5. 5 times 5. I can easily give you 25 examples. Let's see. All they have 107 bond angle, and the shape is trigonal pyramidal. Shape of the molecule is trigonal pyramidal. See that? Okay. Can I rub the board? Now see the examples. I can give you 25 examples. Look at that. Group 5 and 5 elements. So I will give you 25 examples. And all they have bond angle 107 and the shape is trigonal pyramidal. Let's see. Can you give some example? I told you either hydrogen or halogens, which is a monovalent atom. You can use all the halogens like nitrogen, then phosphorus, arsenic, antimony, bismuth attached with 3 hydrogen, NH3, PH3, phosphine, ASH3, arsine, antimony, bismuth, bismuthine, stibine, and bismuthine. All they have, what's the shape and what's the bond angle? Trigonal, pyramidal, and a bond angle 107. How I know? I told you, you have to focus the central atom. If the central atom is from group 5, having 3 bonded pair of electron and a 1 lone pair, then the shape is trigonal, pyramidal, and the bond angle is 107. Now look at that. One more example: nitrogen trifluoride, nitrogen trichloride, nitrogen tribromide, nitrogen triiodide. All they have, you can use all the halogens. So all they have same bond angle and the shape is trigonal bipyramidal. Use the phosphorus, PF3, PCl3, phosphorus trichloride, PBr3, phosphorus tribromide, PPI3 triiodide, AsF3, SbF3, BiF3. AsCl3, that was a past paper question, SbCl3, BiF3, sorry, BiCl3, here AsBr3, SbBr3, BiBr3, bismuth tribromide, last one As triiodide, Sb triiodide, Bi triiodide. Look at that. I told you 25 molecule, 5 times 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You can count 25 molecule. These 325 molecules have same shape, trigonal, pyramidal, and a bond angle 107. One, before I want to stop here, I want to give you one question, guys. That was a past paper question. Look at that question. Just, you can easily answer that question. If you want, you can copy that question with me. The bond angle in methane is 109.5, whereas the bond angle in Ba, in ammonia or NF3 or anything, in ammonia, let's take ammonia, why NF3? In ammonia is 107. Why? Explain. Why there is a difference. Explain why there is a difference. Whenever you come across explain, you can't just write one word. The bond angle in methane is 109.5 because there is no bond pair lone pair repulsion, whereas in case of ammonia, most of the students, they try to mention because of the presence of lone pair. Yes, I do agree, but you have to use the key term. In ammonia, the bond angle is decreased because be a decrease in ammonia, bond angle is decreased in ammonia in NH3. Why? Because there is a repulsion between lone pair and bond pair, LP lone pair and BP. That's why. No doubt, because of the presence of one lone pair, the bond angle is decreases. But what's the actual reason, guys? The actual reason is there is a repulsion between the lone pair and bond pair. The degree of repulsion we work out like this: LP, lone pair, more repulsion. We will come across soon this type of example, which is greater than LP-BP, lone pair, bond pair, which is greater than BP-BP, bond pair. Okay, guys, please keep on watching my videos and I will come back to you very soon. Thank you so much. Hi guys, welcome back to my channel. I've already started shape of the molecule, and please, I'm just requesting you watch my first video of shape of the molecule. Let's do the continuation of the shape of the molecule now. So I have already explained the tetrahedral shape in my previous video and trigonal pyramidal shape for the group 4th element and group 5 element. Now let's see the, sorry, my bad, group 4. Yeah, we have done the group 4, group 5, now group 6 element. Group 6, this is group 6 element. We have oxygen, sulfur, selenium, tellurium, polonium. Polonium is the radioactive, just ignore the polonium. Okay, group 5, we have done it. And group 6. Group 6 element, they have 6 valence electron. What do you mean by valence electron? Valence electrons is nothing but the number of the electrons present in the outermost shell. So they have 6 electrons present in the outermost shell. Okay, if the central atom is from group 6, having 2 bonded pair of electron and 2 lone pair. Now see what will be the shape and what will be the bond angle of these molecules, of these compounds. If the central atom is from group 6, if the central atom is from group 6, having 2 bonded pair of electrons and 2 LP lone pair. If the central atom is from group 6 element and even having 2 bonded pair of electron and 2 lone pair. Look at that. Just we can take the example of water molecule having 2 bonded pair of electron. It has 6 electron, 1, 2, 3, 4, 5, 6. 2 bonded pair of electron and 2 lone pair. Can you guess what will be its shape? Shape can't be linear. We can assume these bonded pair of electrons should be linear, but because of the repulsion between the lone pair and a bond pair, it can't move and make a straight line. That's not possible, guys, because of the lone pair bond pair repulsion. So what will be the shape? It's not a linear shape, so you can say non-linear, V shape, bend shape, angular shape, all are fine. I've seen in many textbooks of OCR, AQA, they have mentioned V shape. At Excel, I've seen in Excel. In Excel, it is mentioned as angular. So V shape, fine. That's the OCR and AQA. V shape, it looks like a V. Look, V shape, non-linear. Yeah, it's not linear, non-linear, due to the presence of lone pair and bonded pair. V shape, the shape of the molecule is the shape of the molecules or compounds. The shape of the molecules, the shape of the molecule is V shape, non-linear, angular, V shape, bent. I've seen in many textbooks bent, non-linear, bent, V shape, and angular. If you're doing OCR and AQA, just mention bent or V shape. Okay, what is the condition, guys? The condition is if the central atom is from group 6 having two bonded pair of electron and two lone pair, then the shape of the molecule is non-linear, V shape, bent. And what about the bond angle? What about the BA, British Airways? Sorry, my bad, just a joke. BA, what's the bond angle? For methane, we have done, for methane, in case of methane, we have four bonded pair of electron and no lone pair. No lone pair, 109.5. And we move from group 4 to group 5, like in case of ammonia, one lone pair, and when the molecule has one lone pair, we have to decrease the bond angle by 2.5 angle. So that become 107. So we have two lone pair. So further, in case of water molecule, you have to decrease 2.5 angle. Just take away 2.5. So how much is that? 104.5. It's easy, guys. No lone pair, perfectly TD. This is TD, tetrahedral, and this is trigonal, trigonal bipyramidal. Sorry, trigonal pyramidal, pyramidal. We will do bipyramidal later on. And this is nonlinear, bent, bent. Not only water molecule. If the central atom is from group 6, like H2S, H2SE, H2TE, tellurium, selenium, all they have nonlinear shape, bond angle 104.5. So we have done. So I have started from group 4, all these, group 5, like these elements, group 6, these elements. Group 5, the central atom is either nitrogen, phosphorus, arsenic, antimony, bismuth. Group 6, any one of this would be the central atom. So what is a central atom? Central atom is only one atom having many, it is bonded by many other atoms. Like I told you, we can use either hydrogen or a monovalent atom. Monovalent means it can form one single covalent bond, like halogens, guys. Fluorine, you can put fluorine, chlorine, bromine, iodine. In place of H2, you can use any of those. The shape will be bent and a bond angle will be 104.5. Agree? Now, after that, I want to slightly move back to group 3 elements. Let's see what will be the shape and a bond angle if the central atom is from group 3. Keep on telling you guys, this type of explanation you can't find in any textbook. I make this shape of the molecule very easy so that everyone can understand and learn how to do the shape of the molecule. We can't memorize the chemistry, guys. I told this sentence a million times. You can't memorize chemistry. You have to understand the chemistry. Like physics, like mathematics, you can't understand the chemistry by memorizing it. Just you have to, sorry, you can't learn the chemistry by memorizing. You have to understand the chemistry, guys. So now, group, I want to move back to group 3 elements or group 3rd. Group 3rd element or group 3 elements. They are placed in group 3 because, now look at that. Group 3 elements: boron, aluminum, gallium. Boron, aluminum, gallium, indium, thallium, TH or TL, carbon, silicon, germanium, tin, PB. Yeah. So group 3. boron. If the central atom is from group 3, if the central atom is from group 3 elements, is from group 3 elements, having 3 bonded pair of electrons. I will write complete electrons and no lone pair, no LP. If the central atom is from group 3 having 3 bonded pair of electron and no lone pair, boron has no lone pair. If boron form any 3 bond like BF3, look at that, it has no lone pair and it can form 3 covalent bond. Look at that one. Boron trifluoride, aluminum trichloride, boron trifluoride. 1, 2, 3. Look at that one. One bond is a planar molecule, guys. It's not the 3D, just planar molecule. So we are not using the wedge and dotted. This is a planar molecule. Look at the planar molecule. B boron, 1 fluorine or hydrogen. You can use a fluorine. You can use chlorine also, a fluorine. Okay. So if the central atom is from group 3, having 3 bonded pair of electron and no lone pair. Look at that. You look at that. Like this. This is a planar, like the whiteboard. Look at that. That's the planar molecule, guys. Look at that. This is the planar molecule, like this. Or you can imagine that's the wheel of the car. Look at that. It's the wheel of the car. It is like this. It's a planar. Ammonia is 3D, and this is the planar molecule. Look at that. This is the planar molecule, like this. Okay. My hand, assume that this is the board. My hand is like a board, and this is the planar molecule. It's not the 3D. This is the planar molecule. Yeah. And these are at the equidistance. B and F bond is at the equidistance. So what will be the bond angle? The total is 360. Total, all these circles is 360, and you have to divide it by 3 because of 3 bond. 360 divided by 3 is 120 degree, guys. Yep, like this. This bond angle is same as that one, is 120. So if the central atom is from group 3 having 3 bonded pair of electron and no lone pair, the bond angle is 120. And what's the shape? It's planar. Ammonia is also a planar, but because of the presence of the lone pair, it becomes pyramidal. This is not a pyramidal, just trigonal planar. Trigonal planar. Planar molecule, not the 3D shape. If assume that if I pull the boron and lift it up, like for example in case of ammonia, this is like a, this is, you have to visualize, guys. This is like this. So this is that one. It's like this. Okay. And I'm going to pull the tie the boron or any element and try to lift it up. When you put it apart, the bond, these bonded pair of electron and the bonds move like this. If you pull it like this, and it become like a trigonal pyramidal, like a tripod of the what can I say, is a tripod stand for iPhone, for anything. It become like this. So this is a pyramidal shape, and if I press this central atom, it becomes flat. Press it, and that becomes flat. This is a flat molecule. Flat molecule is planar molecule. Look at that one. So this is BF3 or BCl3, whatever may be. Yeah. So if the central atom is from group 3, because it has no lone pair, having 3 bonded pair of electrons and no lone pair, then the shape of the molecule is trigonal planar and the bond angle is 120. Any more example? Instead of fluorine, you can use chlorine, you can use bromine, BBr3, you can use iodine, trichloroboron, tribromoboron, triiodoboron, same shape, same bond angle. AlCl3, what's the shape and bond angle of AlCl3? Aluminum trichloride. What's the shape and bond angle, guys? The shape is trigonal planar and the bond angle is 120 degree. When you will come across the question based on the shape of the molecule, try to identify or try to pick the central atom. All the story is moving around the central atom. If the central atom is group 4, we have done it. If the central atom is group 5, we have done it. I want to give you a small gist kind of stuff. Then I'm going to teach you the linear molecule after that, and a molecule with double bond and a triple bond. Let's do that one. Yeah, the group 4, group 4, group 5, group 6. We are not doing group 4, group 5, group 6, and group 3. Why group 3, sir? I'm moving back. So I'm moving forward, then going back, because the number of lone pair increases. No lone pair. Yeah, 4 bonded pair of electrons. 4 bonded pair of electrons. No lone pair. No LP. No lone pair, guys. No LP. No LP. You know, group 4 elements. Look at the periodic table. What are they? Carbon, silicon, germanium, tin, SN, PB. Yeah, PB is the radioactive, just ignore the PB. Okay, now group 4. 4 bonded pair of electron, no lone pair. Shape and bond angle. Shape is perfect tetrahedral, perfect tetrahedral. Geometry is tetrahedral, and a bond angle, it's 109.5. No lone pair, 4 bonded pair of electron, and a bond angle is 109.5. Now group 5, nitrogen, phosphorus, arsenic, antimony, bismuth. 4 bonded pair of electron, 3 bonded pair of electron, 1 lone pair. 3 bonded pair of electrons, 1 LP. No lone pair, 1 lone pair. Look at the bond angle and shape change from no lone pair to 1 lone pair. Shape of the, I'm not writing shape. That is shape is, I'm not writing. Shape is trigonal, pyramidal. Trigonal, pyramidal. You have to decrease the bond angle. 109.5, take away 2.5. So 107. Group 5, then the group 6, group 4, group 4, group 5, group 6. Group 6, oxygen, sulfur, selenium, tellurium, polonium. 2 bonded pair of electron, 2 bonded pair of electron. I'm sorry, I forgot the drawing, guys. Like me saying. This is wedge bond. and this is dotted at the back. Ammonia also, two wedge, one dotted with lone pair. Hydrogen, hydrogen, hydrogen. If the central atom is from oxygen, sulfur, selenium, tellurium, polonium, two bonded pair of electron, two bonded pairs of electron, two lone pair. Instead of one lone pair, it has two lone pair, 2lp. 0lp, no lone pair, 0 lone pair, 1 lone pair, 2 lone pair. Look at that. So the shape of the molecule or compound is bent, V shape, bent and V, both are fine. What's the bond angle? Take away minus all the time. Minus 2.5, guys. Minus 2.5. Minus 2.5. So how much is that? 104.5. Bent water molecule, best example, with two lone pair and two bonded pair. One lone pair here, one lone pair here, one lone pair here. The bond angle is 104.5. Bent, V shape, last one. Group 3, if the central atom is from group 3, obviously it has no lone pair, 3 bonded pair of electron, 3 bonded pair of electron and no LP. So look at the difference between the group 5 and group 3. Group 5, 3 bonded pair of electron, undoubtedly 3 bonded pair of electron, 1 lone pair, make the molecule 3D, no lone pair, make the molecule 2D, flat molecule, trigonal, pyramidal, no lone pair, what's the shape? Trigonal, planar. Bond angle, exactly 120. I will draw it, BF3. Boron trifluoride, 1, 2, it's like a wheel of the car. So look at that one. 120 degree. So shape, we know the bond angle is BA, bond angle 120 degree. So that's the small gist, and you will come across many questions from these group 4, group 5, group 6, group 3. And it's easy to remember that one. And if you want to write down on your flash card, and that will be good for you guys. So I want to stop my video here, guys. Thanks for watching my video, and I will come back soon. Hi guys, welcome back to my channel. Let's start today's topic. You know, I've already discussed the shape of the molecule in my previous video, and we have already discussed the shape of tetrahedral complex, trigonal planar complex, trigonal pyramidal complex, and non-linear shape. Now see that when we have a double bond or a triple bond, please try to ignore the double bond and a triple bond when you consider the shape of the molecule. So the double bond and a triple bond will not help to figure out the shape of the molecule. So try to ignore the double bond and triple bond. So we didn't get it. Okay, now look at that. Carbon with oxygen. Look, carbon has 4 electrons in the valence shell. It has 4 electrons, 1, 2, 3, and 4. Okay, and oxygen has 6 valence electrons. For oxygen to get the 8 electron in the outermost shell, each oxygen atom share 2 electrons. Look at the 2 electrons. So this oxygen, it has 6 electrons, 1, 2, 3, 4, 5, 6. So it will share 2 electrons with the carbon. And 1 more oxygen atom. Look at that. 1 more oxygen atom. 1, 2, dot and cross. 1, 2, 3, 4, 5, 6. So in most of the cases, when oxygen combines with the carbon, oxygen either form a triple bond or a double bond. not a single bond. That is not possible, guys. This is not a right structure. Oxygen with a carbon, there will be no single bond. It is always a double bond or triple bond, like in case of carbon monoxide. Now look at that. So oxygen, look at the sharing. Oxygen form double bond with carbon. Each carbon share 2 electron, because carbon has 4 electron in its valence chain. So oxygen form a double bond with the carbon. This is an example of carbon dioxide. That's the carbon dioxide, CO2. So in CO2, each oxygen form a double bond with the carbon. Now I told you, note, please note it down, that one. Ignore double and triple bonds when we draw the shape of the molecule. When we work out the bond angle of any compound, you have to ignore the double bond, like pi bond. Just ignore it. When you ignore it, how the molecule looks to you? There is a double bond, but just ignore when you work out the shape of the compound. So it looks like a linear compound. Yeah, non-linear because the water molecule has 2 lone pairs. So there is no lone pair bond pair repulsion. Do a double bond create any lone pair bond pair repulsion? No. No repulsion of these electrons, of these bonded pair of electrons. So no repulsion. One more question will come in the mind. Can a pi bond, can a double bond or a triple bond affect the shape of the molecule? No. It may affect the bond length, but we are not discussing the bond length. Yeah, but the bond angle is fine. No problem created with the pi bond or with the double bond and triple bond or on the shape of the molecule. So just ignore the double bond and a triple bond. Now look at that. It look linear to me. Linear. What's the bond angle? 180 degrees. Look at that. So what is the example of a linear compound? Carbon dioxide, CO2. What's the bond angle? What's the shape? Shape of CO2, linear, perfect linear. And what's the bond angle? BA, bond angle 180. Now, can we do the triple bonded compound? Yes, we can do the triple bonded compound. So double bonded compound, we have done it. Now triple bonded compound. Guys, any example for triple bonded compound? I want to do one more example for double bonded compound. Yeah, that's I have seen in some past paper. Ethene. Look at the ethene molecule. C2H4. Not ethane, ethene. So that's alkene. Alkene is a hydrocarbon in which there will be at least carbon-carbon double bond. I will teach you guys when I will make videos on organic chemistry. Look at the structure. That's the ethene. There is a double bond between carbon and carbon. Okay. Now, I told you just ignore. So we will do what's the shape and bond angle of question. What's the question? What is the shape and bond angle of first A, we have done carbon dioxide just now, B, ethene, C, hydrogen cyanide, HCN. Now look at the ethene. Look at each carbon. Each carbon make 4 bond, 1, 2, 3, 4. And I told you, ignore pi bond or double bond. Just ignore it. So each carbon make 3 bonded pair of electron, 3 bond and no lone pair. Is that okay? It has 3 bonded pair of electron and a no lone pair. Look, each ethene molecule has 3 bonded pair of electron and no lone pair. I know there's a double bond. It is a planar molecule. So we have done like a BF3. We have done the shape of the BF3. Boron has 3 valence electron and it can form 3 bonds. So in case of boron, we have seen 3 bonded pair of electron and no lone pair. Very similar condition, 3 bonded pair of electron and no lone pair. So the shape of the molecule is trigonal planar and the bond angle is 180. Look at that. The shape of the molecule is trigonal planar and the bond angle is 120 degree. 120. Okay, each carbon, we are talking about the each carbon, 120. And what's the bond angle? 120. Shape of the molecule, shape of C2H4 is trigonal planar. Trigonal planar, and the bond angle is 120. Planar. I want to discuss one more, hydrogen cyanide. Look at the hydrogen cyanide. Okay, can I rub the board? Look at the hydrogen cyanide. What's the shape? Hydrogen cyanide, HCN. Carbon and nitrogen. Nitrogen has 5 valence electron. Look, carbon form 1 bond with hydrogen. Carbon can only make single bond with hydrogen and 3 bonds with nitrogen. Hydrogen cyanide. I told you, ignore this bond, ignore this bond. How the molecule looks to you guys? It looks like a linear molecule. Visualize that one. It is like a linear molecule. Yeah. Linear. Bond angle 180 degree. Linear molecule. What's the shape? Linear. Bond angle 180 degree. Okay. Now, any more example for linear molecules? All they have double bonded and a triple bonded with no lone pair. Any compound which has double bond or a triple bond can be a trigonal planar or a linear. I will give you one more example, guys. Look at that. CH3, C double bond O, OH. This is ethanal aldehyde. Ethanal. ETHANAL. Ethanal, not ethanol, ethanal. It's an aldehyde. Look, each carbon make 1, 2, 3. I told you, ignore it. Ignore that double bond. So carbon has 3 bonded pair of electron and no lone pair. So what's the shape? Shape is trigonal planar. And bond angle 120. Look at that. So double bonded compound we have seen and triple bonded compound we have seen. Now some of the what we call some of the special categories, like they are not following a normal trend. So we do like not from the trend, like a trend mean like a group 4 element, group 5 element, group 6 element, and I have done the group 3 element, some specific shapes. Okay, I will come to shape of the ions. First, let me teach you all the molecules which which I have seen those examples in many past papers. Yeah. Now one more. Look at that. What is the shape and bond angle of PCl5? PCl3 we have discussed. PCl3, one lone pair, three bonded pair of electrons. We've already discussed PCl3 when I have discussed group 5 elements. One lone pair and three bond pair, trigonal, pyramidal. Now this is different one, PCl5. Now phosphorus has how many electrons in the valence shell? 5. 1, 2, 3, 4, 5, and they all share with 5 chlorine. Do cross chlorine. That's okay, don't cross structure, but we can't predict the shape of the actual molecule and the bond angle. Now look at that. Look at that, guys. This is a planar trigonal, like this is a trigonal planar structure. Look at that. It's like this and like that one. Same thing, it's a planar structure. So I have phosphorus at the center. Look at that. This is phosphorus. P. It has one chlorine at the corner. Corner chlorine. There's a chlorine at the corner. Corner we have chlorine. Look at that. At the corner we have chlorines. So phosphorus, this is P, chlorine, one chlorine. Okay. Now after that, it's like a planar molecule. How the two more chlorine oriented? Look at that. The two more chlorine is oriented like this, which is perpendicular to this plane. Look at that. So actually this is a 3D shape, and I can draw it, but you can't visualize from the board. So try to visualize that one. So it's the center one. I have phosphorus. That's the phosphorus. One chlorine, and the top we have one more chlorine, and the bottom we have one more chlorine. It looks like that. So I will try to draw it, how it will look like, and then we can visualize and find out the shape and the bond angle. Look at that. So this is trigonal planar compound, which is P chlorine. Now two more chlorine, they are perpendicular. Look, chlorine and chlorine, they're perpendicular. Look at that. They are perpendicular. So can you guess what is the shape of PCl5? Look, I try to tie some string here. I tie some string, and it looks like a pyramidal. Look at that. It looks like a pyramidal on the top, and one more pyramid at the bottom. So look at that. Assume that we have a string and we hold it like this. So this is one pyramid from the top, and this is one pyramid from the bottom. So the shape is trigonal. This is trigonal, bipyramidal, and it has two bond angles. Look at that. The bond angle, we know that bond angle. This bond angle is 120 degree, and that's the 90-degree bond angle. What's the 90-degree bond angle? That's a perpendicular. So what's the bond angle? 90 degree. So we have two bond angles. One bond angle is this one, which is 120, and this one is 90°, which is perpendicular. So that's the shape of PCl5. They can give you PBr5. So instead of chlorine, you can use any halogen. Phosphorus, possible. Do we have NCl5? No, not possible. We cannot have NCl5. Why we cannot have NCl5? Why there will be no compound such as NCl5? I will give you this as a question, so you have to figure out. There will be PCl5. There is a PCl5. All like 5 halogens are there for look at that. So phosphorus can form PCl5, PCl3 as well as PCl5. Phosphorus, arsenic can form ACl3 and PCl3 and all the halogen. Sb can form SbCl3 and SbCl3 and SbCl5, but not for nitrogen. Nitrogen cannot form pentachloride. There's no nitrogen pentachloride. But phosphorus can form pentachloride, arsenic can form pentachloride, bismuth antimony can form pentachloride. And what is the shape of the molecule? Trigonal bipyramidal, and it has 2 bond angle, 120 and 90°. Look at that, guys. Look at that. You can visualize like this. So what was the bond angle? What's the shape of the molecule? What is the shape of the molecule? So the shape is trigonal pyramidal, and the bond angle is we have 2 bond angle, 120° and 90°. Look at that. Shape of the molecule. Shape of the molecule. Molecule or compound. Trigonal bipyramidal. And what's the bond angle? We have 2 bond angles. 120° bond angles, BA, 120 and 90. Okay, let's do one more compound, and that's one of the favorite compounds. My next compound is one of my favorite compound. Let's do that one. Look at that. That is SF6. So what is the shape and bond angle of SF6? Let's do the SF6 molecule. Shape and bond angle of SF6. What is the shape and bond angle of SF6? Sulfur hexafluoride. Sulfur can make 6 bond. No lone pair. All 6 bond. We can visualize from that. First of all, we have a square planar molecule, SF4, like square planar molecule. Look at that. This is square planar. I want to draw the square planar. Sulfur is here. We have fluorine. One fluorine and a fluorine. This is a square planar molecule. And a 2 more bond. One at the top, 1 bond coming from the top, F, and 1 bond from the bottom, F. So look at that. So that's a planar molecule. This is like a planar molecule. And we have 1 bond at the top and 1 bond at the bottom side. So how many faces it has? Look at that, guys. Please try to visualize. If you can't visualize, it's hard to memorize a compound. 1 bond here, 2 bond, 3 bond, 4 bond. 4 bond from the top and a 4 bond from the bottom. 1, a 2, a 3, a 4. So it has 8 faces. It has 8 faces, guys. Look at that. One face from that side, one face from that side. So one, this one, 2, 3 at the bottom, 4. In the same way, 1, 2, 3, 4. It looks like a complicated structure. It has 8 faces. So the molecule which has 8 faces, what will be its shape? The shape of the molecule is octahedral, like a tetrahedral. This is octahedral complex, SF6, or compound. SF6 is a octahedral molecule. Sorry, my bad, I use the term complex. We will do the complex when I will teach you transition metal. So we have different shape of the complexes also. So this is octahedral molecule. Now, can you let me know what's the bond angle? What is the bond angle? Look at that. What's the bond angle? Each corner, you know that each corner is 90 degree, 90 degree, 90 degree, 90 degree. One of the past paper question, give the example of a molecule having 90 degree bond angle. So 90 degree bond angle, 90 degree. You can get this kind of question also. What is the bond angle between this fluorine, sulfur, fluorine? What's the bond angle? 180 degree. Mostly they will ask what's the bond angle. You can mention 90 degree. If you will get a question specifically, what is the bond angle between sulfur, fluorine, and sulfur, then you can say 180 degree. Otherwise, that's fine. SF6 molecule. So instead of fluorine, can we take any other halogens? You can take SCl6, but I haven't seen SCl6 compound. SF6 is a common compound, a very famous compound. So the shape of the molecule is the shape of the molecule is octahedral, and a bond angle is 90 degree. Okay, so I try to discuss all of the molecule which I came across from the different past paper. We have to do shape of the ions and some more specific example. So guys, I want to wind up my video here. I will come back with the next video. Thanks for watching. Hi guys, welcome back to my channel. You know that in my previous videos I have discussed the shape of the molecules, but I didn't start the shape of the ions. I've discussed tetrahedral shape, trigonal pyramidal shape, bent shape or V shape, trigonal planar shape, trigonal bipyramidal shape, octahedral shape. Let's continue some more example of shape of the molecules. Look at that one. I've already discussed SF6, which is octahedral. Now SF4. What is the shape and bond angle of SF4? Let's do the SF4 molecule. Sulfur tetrafluoride, SF4. Shape and bond angle of SF4. Do you have any idea about the shape and bond angle of SF4? Let me draw first. Sulfur is the central atom. 2 fluorine. Sulfur has 6 valence electron. 1 goes back into the white boat or the behind the boat, and 1 is like this, like a wedge. F. Sulfur has 6. 1, 2, 3, 4, a 5 and a 6. 2 electron left on it. So let me know what's the shape. Any idea? So it looks like a seesaw shape. One bond angle is 86.5, and one is 102. Okay. Now I have some more molecule like chlorine trifluoride. Let's see the chlorine trifluoride. Look, chlorine trifluoride. fluoride. Chlorine has 7 valence electron, and then make 3 bond with fluorine, 1, a 2, a 3. 3 bond with fluorine. How many electron left? 1, 2, 3 gone. 4, 5, 6, 7. How the shape looks to you guys? T shape, important. That was a past paper question. T shape, T shape. Bond angle 87.5. Now some more molecule like chlorine pentafluoride, like chlorine trifluoride. In the same way, chlorine pentafluoride. Look at the shape and bond angle of chlorine pentafluoride. Yeah, let's see the bond angle and the bond angle and shape of the chlorine pentafluoride. Okay, chlorine pentafluoride. Look at the chlorine. Chlorine has 7 valence electron in the outer shell. So one, look at that. Chlorine, 1 bond here, 1 bond here, 1 here, 1 here, 1 at the top. Fluorine, yeah. How the molecule looks to you? Isn't it like a pyramidal shape? Like it's like a pyramid. It's like a pyramid. So in case of ammonia, we have seen trigonal, pyramidal, but this is square planar pyramidal. Yeah, unique molecule, very unique molecule. Square planar pyramid, and the bond angle is 90 degree, guys. 90. BA bond angle 90 degree. Now, so we have done Cl3 chlorine trifluoride T shape, Cl5 square planar pyramidal. Now xenon tetrafluoride. Look at the xenon tetrafluoride. XeF4 xenon tetrafluoride. What is the shape and bond angle? Xenon tetrafluoride. XeF4. Look at that. Xenon has 6 valence electron. So that 2 bond coming out of the plane with a thick wedge, and this is the dotted wedge going behind the board or behind the plane. A fluorine, and a 2 lone pair. This is the plane and 2 lone pair. One at the top, one at the bottom. The arrangement of those 2 lone pair will not affect the bond angle and the geometry. Look how it looks to you guys. This is at the bottom. This lone pair at the bottom, that lone pair at the top. So it's like a plane. It's like a plane molecule. One lone pair at the top, one lone pair at the bottom. The arrangement of the lone pair is in such a way that it won't create any lone pair bond pair repulsion. The bond angle is 90 degree. 90 BA bond angle 90 degree, and the shape of the molecule, any guesses? Square planar. Yep. Now SO3 and SO2. Let's do the SO3 molecule, sulfur trioxide and sulfur dioxide. Shape and bond angle of SO2 and SO3. Shape and bond angle of SO2 and SO3. Sulfur trioxide and sulfur dioxide. I want to compare. Look at that. Sulfur has how many electrons in the valence shell? 6. And oxygen make always a 2 bond, double bond. Oxygen is a divalent, so it always make a double bond with the sulfur. SO3. I told you 3 bond pair and a non-lone pair. I told you you have to ignore pi bond. Trigonal, trigonal, planar. But the bond angle is not exactly 120. It's greater than 120. So you can put like greater than 120 degree. Now SO2, sulfur dioxide, 2 double bond. Sulfur has 1, 2, 3, 4, 5, 6 lone pair. Yeah, in that case, the pi bond and a lone pair, there will be no repulsion between the pi bond and a lone pair. So the bond angle is 120 degree, but the shape is not trigonal planar. It is like a bent shape, 120 degree, and the shape of the molecule bent. Here, the lone pair and the double bond will not cause any repulsion. So that's why the bond angle is 120 degree. But the normal bent molecule, the bond angle is, in case of the normal bent molecule, the bond angle is 104.5. Look at the water molecule, which is a bent molecule, and it has 2 lone pair. And that molecule has a maximum lone pair bond pair repulsion. That's why the bond angle further decreased from 107 to 104.5. 104.5. The bond angle in ammonia is 107 because of the presence of 1 lone pair. Okay, now let's see shape of ions. Ions, they have either positive charge or negative charge. How those positive charge and a negative charge affect the geometry and a bond angle. Let's see. Normally the positive charge has no influence, guys. Like a pi bond, like a double bond and a triple bond, there is no effect of positive charge on the shape and the bond angle. Now, but the negative charge, that causes a repulsion, because the negative charge is nothing but a pair of electrons. So because of the presence of the negative charge on any molecule or any ion, that distort the bond angle, distorted means change its bond angle, and also affect the shape of the molecule. Let's see. First, we will do with ammonium, positive ions. Ammonium ion, NH4 plus. Whenever we have a positive charge, we end by EM, ammonium. Shape and bond angle of ammonium. Ammonium. It has a dative bonds. Ammonia has a 3 covalent bond. Ammonium ion has a 1 dative bond. So I have already discussed that ammonium ion in my previous video. Now let's see the shape and a bond angle. Now look at the ammonia. It has 3 bonded pair of electrons with 1 lone pair. Agree? It has 3 bonded pair and 1 lone pair. Whatever the lone pair it has, it is donated to hydrogen. Now, with the positive charge, because nitrogen lost a pair of electrons. Now, look at that. In this case, nitrogen make 4 bonded pair of electron and no lone pair, which is closely look to the to the methane molecule. Like, look at the methane molecule. We have to always go back and check our parent compound. It looked like our parent, one of the parent compounds. So central atom, don't worry about the carbon and a nitrogen, but in case of methane, central atom has 4 bonded pair of electron and no lone pair. I told you, if a central atom has 4 bonded pair of electron and a no lone pair, then the shape of the molecule is, any idea? Tetrahedral. And what is the bond angle? 109. 109.5. Shape it's same as methane molecule, tetrahedral, and a bond angle 109.5. Okay, ammonium ion. Why the ammonium ion is related to methane? Because of the same condition. What's the condition? Central, don't worry about the central atom. So central atom here is from group 4, but here no doubt central atom is nitrogen. It has 4 bonded pair of electron and no lone pair. Now hydronium ion, H3O plus, a dative bond. Look at the shape and bond angle of hydronium ion. Hydronium ion, hydronium ion. All the positive ion we ended as neum, eum. Okay. Look at the hydronium ion. The water has 2 lone pair. Out of 2 lone pair, oxygen donated one of the lone pair to H plus ion. Look at the drawing first. Oxygen has 2 lone pair. In case of the water molecule, one of the lone pair given to H plus ion. Dative bond. This is the positive charged ion, put plus side on it. Now, can you remember or can you recall that shape is similar to this compound, guys? 3 bonded pair of electron and 1 lone pair. Nitrogen has 3 bonded pair of electron and 1 lone pair. Similar structure, 3 bonded pair of electron and 1 lone pair. What is the shape of ammonia and bond angle of ammonia? We know that. Trigonal, pyramidal. Here same, trigonal, pyramidal, bond angle 107, 107. 3 bonded pair of electron and 1 lone pair. Can you do this question? What is the shape and bond angle of CH3 minus ion and CH3 plus ion? Look at the CH3 minus ion. CH3 carbon make 3 bonds with hydrogen and having a negative charge. I told you just now, negative charge is nothing but a pair of electron. So this negative charge, you assume that there is a pair of electron. So negative charge appear as a pair of electron. Now look at that. So carbon has 3 bonded pair of electron and 1 lone pair. It quite resembles to ammonia, guys. Look at that. It's resemble to ammonia molecule. Has 1 lone pair and 3 bonded pair of electron. Hydrogen, hydrogen, 1 more hydrogen. Look at that. 3. Because negative charge is nothing but a pair of electron, so there is a lone pair bond pair repulsion. It looks similar to ammonia. 3 bonded pair of electron, 3 bonded pair of electron, and a lone pair. So you know that. What's the shape? trigonal pyramidal bond angle 107. You know guys, negative charge carbon is called carbanion. And let's see the positive charge carbon. Shape and bond angle of CH3 plus. Now it's a shape and bond angle of CH3 plus. Carbocation. Positive charge carbon is called carbocation. Carbocation. Shape and bond angle of CH3, a positive charge. So carbon, hydrogen, 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 and a plus charge. I told you just now, positive charge has no electron. Positive charge compound are deficient of electron. So there will be no repulsion between this bonded pair of electron and a positive charge. So if a molecule has a positive charge, ignore that positive charge. Like a pi bond and a double bond, it has no influence on the shape of the molecule and the bond angle. So look at that. It is similar to, try to recall the parent one. It is similar to BF3 guys. Boron trifluoride. 3 bonded pair of electron, no lone pair. Carbocation. Methyl carbocation. Methyl CC. Carbocation. Very similar to BF3. So we have discussed the shape and bond angle of BF3. Shape is trigonal planar and bond angle is 120 degrees. Same thing. Shape is trigonal pyramidal, trigonal planar, and a bond angle BA 120 degrees. So just I want to finish my video here, and I will come back with some more example of molecules having ions ions having negative charge or the positive charge. Thanks for watching. Okay. Hi guys, welcome back to my channel. You know, I've already started shape of the molecule and I have discussed almost all the molecule. I found some of the molecule I left which I want to discuss today. That molecule normally came in the past paper. So let's discuss a few of the molecule, and hopefully that's my last video on the shape of the molecule. Look at that. That's one question, like what is the shape and bond angle of BF4 minus boron trifluoride. Let's start with the boron trifluoride, which is trigonal planar. Boron has 3 valence electron, but here one of the fluorine give a pair of electron to boron. Look at that one, boron trifluoride, and that's the overall charge, guys. This is the overall charge. This charge, a negative charge, is not present on the boron. And we discussed like Vesper theory, valence, electron pair repulsion, VES repulsion theory. According to that theory, any negative charge acts as a lone pair, and if that negative charge present on the central atom, that negative charge definitely influence bond angle and the shape of the molecule. Valence shell electron Vesper theory, valence shell electron repulsion theory, VES Valence, VESPER, whisper theory, valence electron shell repulsion, shell electron pair. Look at that. Valence shell electron pair repulsion theory. According to that theory, any negative charge which act as a lone pair, if that negative charge or a lone pair present on the central atom, that will definitely create a disturbance or distraction in the bond angle and the shape of the molecule, or that will definitely affect the bond angle and the shape of the molecule. But here the negative charge is not present on the central atom. This negative charge is the overall charge. So this Bf4 minus is closely resembles to methane molecule structurally, not in the chemical functionally, not in the chemical properties and the physical properties, only similar to methane molecule. Look, Bf4 minus is closely related to structurally methane molecule. Central atom is carbon in case of methane molecule. So central atom, like carbon, having 4 bonded pair of electron and no lone pair. I'm keep on telling you guys, lone pair, there's no lone pair, and the central atom has no lone pair. This negative charge is not present on the boron. So look at that. It's a tetrahedral shape. What's the bond angle and the shape of the molecule? Bond angle BA 109.5, and the shape, any guesses? Tetrahedral. Shape of the molecule, it's TD, tetrahedral. Okay, now can I rub the board, guys? Now look at that. We will do some past paper question of the shape of the molecule and the bond angle of some questions. Now look at that. Predict the shape and bond angles. Predict the shape and bond angle. Predict the shape and bond angles of the following. H2S A, H2S, AlCl3, AlCl3, Si, F4, and last one is PH3. Central atom is from group 6, sulfur, having 2 lone pair of electron and 2 bonded pair of electron. So what's the shape and bond angle? When it has 2 bonded pair of electron and 2 lone pair, bent V shape, bent V, non-linear, 104.5. AlCl3, aluminium is the central atom. Aluminium has 3 electron in the outer shell, 3 valence electron, and it can make 3 bond. AlCl3 3 bonds. So it has 3 bonded pair of electron and no lone pair. Trigonal, trigonal, planar. And what's the bond angle? 120 degree. So in case of SiF4, central atom is from group 4. Silicon has 4 electron in the outermost shell. So 4 bonded pair of electron and no lone pair. Silicon tetrafluoride, 4 bonded pair of electron and no lone pair. Central atom is from group 4, 4 bonded pair of electron and no lone pair. So what's the shape? Closely related to methane molecule. Tetrahedral. Tetrahedral. What's the bond angle? 109.5. Any guesses for pH3? pH3 is similar to ammonia molecule. Phosphorus, central atom is the phosphorus, having 3 bonded pair of electron and 1 lone pair. 3 bonded pair of electron, hydrogen, hydrogen, pH3 is phosphine, hydrogen and 1 lone pair. 3 bonded pair of electron and 1 lone pair. Shape of the molecule is trigonal, pyramidal. Bond angle, any guesses? From 109.5, 4 bonded pair of electron, no lone pair. When a molecule has 1 lone pair, so we have to subtract 2.5 bond angle. So it will be 107. Okay, we will do one more question. Can I rub the board? Okay, one more question. Predict the shape and bond angle of the following. Predict the shape and bond angle of the following. Predict the shape, predict the shape and bond angle of the following. A, hydrogen cyanide HCl. B, NH2 and negative charge. NH4C, ammonium ion, NH4 plus. D, H3O plus. E, ammonium, hydronium, ethene, C2, H4. F, CH3, this is at the null, so you have to work out here for central atom. Now for methane here, CH3 at the null, methanol or ethanol, no worries. So you have to work out here shape and bond angle. PO4 3 minus overall. Yep. Now we will do one by one. HCl, hydrogen cyanide. There is a triple bond between carbon and nitrogen. How the molecule looks like to you guys? I told you, ignore pi bond, ignore double bond. So the molecule look like linear, and the bond angle is 180. That's a tricky. NH2 minus. Look, nitrogen, in case of ammonia, it formed three bond with three bonded pair of electron, but it formed only two bond pair, and ammonia has already one lone pair. In case of ammonia, central atom, that nitrogen has one lone pair and one more negative charge. Negative charge acts as a lone pair. So it has two lone pair and two bonded pair, just like a water molecule. So what's the shape? Bent, non-linear, 104.5. Most of the students, they are getting confused with this molecule. So it looks like structurally it is similar to water molecule. Now some more. Ammonium, I have already discussed ammonium. Ammonium ion, nitrogen. In case of ammonium ion, nitrogen make four bonded pair of electron and no lone pair. Look at nitrogen has four bonded pair of electron and no lone pair. The positive charge is, first of all, it's overall, and it is not on the central atom. Even though the positive charge is present on the central atom, it won't causes any deviation in the bond angle or any change in the shape of the molecule. Okay, so four bonded pair of electron, no lone pair. Shape is tetrahedral. Bond angle 109.5. Now hydronium, hydrogen, what oxygen has two lone pair, but one of its lone pair donated to H plus ion. So one lone pair, three bond pair, and the overall charge is positive. It is similar to the shape of the hydronium ion is closely related to ammonia. I'm talking about the shape, guys. So three bonded pair of electron and one lone pair. Trigonal, pyramidal, and a bond angle is 107. Now ethene molecule, ethene, shape and bond angle of ethene. Ethene has one double bond, carbon-carbon double bond. Now ethene has carbon-carbon double bond. Look, it's a flat molecule, planar molecule. Each carbon has three bonded pair of electron. Pi bond will not affect the bond angle and shape. So carbon has three bonded pair of electron and no lone pair, which is closely similar to BF3. So what's the shape? Trigonal planar, and bond angle 120 degrees. Now in case of ethanal, it's an aldehyde, guys. We have to work out here only for central atom carbon. I'm not talking about this carbon. This carbon is like a methane, four bonded pair of electron and no lone pair. So tetrahedral. This is tetrahedral. I'm talking about this. Oh, let me draw again. I am talking about, look at that. Ethanal, aldehyde. So I gather all these questions from different past paper, AQA, OCR, Edexcel. Now, ethanal, CH3 carbon has double bond with oxygen and one single bond. Look, that carbon, we're talking about that carbon. One bonded pair of electron. This is also bonded pair of electron. This is also bonded pair of electron. Ignore the pi bond. Don't worry about the pi bond. So central atom is the carbon having 3 bonded pair of electron and no lone pair. Similar to that one. Trigonal, planar, 120 degree. Trigonal, planar. Look at that one. Okay. Now, very tricky, guys. I'm putting some asterisks on it because it's a tricky molecule. Most of the student, they say linear. Now, look at the central atom. I always tell you, focus on the central atom. So central atom is from group 6, having 2 lone pair and 2 bonded pair. Structurally, this methanol is similar to water molecule. So look at here. Oxygen has 2 lone pair and 2 bond pair. It's very close to the water molecule, which is a bent molecule, 2 lone pair and 2 bond pair. This is also like a water molecule, so bent, non-linear, 104.5. When I rub the board, I accidentally rub one of my molecule, like phosphate ion, come from phosphoric acid. That's the last molecule. Okay, did you get it? Yeah. Now the last one, phosphate ion. Phosphate ion come from phosphoric acid. Phosphoric acid, what is the chemical formula of phosphoric acid? H3PO4. H3PO4. So central atom has phosphorus with a double bond with oxygen, O hydrogen, OH and OH. Phosphoric acid is an acid. Acid has the ability to give away the proton. So it can give away 3 protons. It's a tribasic acid. Look at that. When it gives away 1 proton, it has 1 negative charge. So in case of phosphate ion, H3, in case of phosphate ion, PO4 minus. In case of phosphate ion, PO4 3 minus. It gives all of 3 hydrogen. Look at that. Phosphate, P double bond O a negative charge, O a negative charge, O a negative charge. There will be no negative charge on the central atom, guys. Central atom is phosphorus having 4 bonded pair of electron. Even though if you ignore the pi bond, 1, 2, 3, 4 bonded pair of electron and a no lone pair. So it's structurally similar to methane. Similar to methane molecule. 4 bonded pair of electron, no lone pair. So what's the shape? What's the shape of methane molecule? Why I'm keep on telling you go back and check the parent molecule. That's the parent molecule. What's the parent molecule? Methane. So methane, we know the structure, we know the shape and a bond angle. Tetrahedral, and bond angle 109.5. So I want to stop here. Thanks for watching my video. I will come back soon. Guys, welcome back to my channel. Today I'm going to teach you chemical today I'm going to teach you covalent bonding. I've already started ionic bonding. So what's going on, guys? Are you enjoying your summer break? Yeah, let's focus on covalent bonding. Covalent bond. We have seen in case of ionic bond, metal lose electron and non-metal gain electron. Okay, so a type of bond is present between metal and non-metal is ionic. Now think over it, how a covalent bond is formed. So let's imagine I have two non-metals, chlorine and chlorine, chlorine and a chlorine. Both are non-metals. How many electrons are present in the outermost shell of the chlorine? Any guesses? Any idea? 7. Yeah. Chlorine is from group 7. It has 7 electrons in its valence shell. 1, 2, 3, 4, 5, 6, 7. And this chlorine has also 7 electrons in its outermost shell, which is called valence shell. And these electrons are called valence electron. Can this chlorine donate electron? And can this chlorine gain the electron? No. Not this type of complete transfer of electron take place in case of two non-metals. Then what they will do? We know non-metal can't lose electron. Can they gain the electron? Yes, they can gain the electron only when they can accept a pair of electron from the metal. But in case of both the non-metal, they can't gain the electron. So what is the alternate choice? The alternate choice for both of them is to share a pair of electrons. So a covalent bond is formed by simple sharing a pair of electrons between two non-metals. So it is a type of chemical bond. It is a type of chemical bond which is formed between two non-metals. How they form means how it is formed by mutual sharing a pair of electron. So we come to know that they can gain a pair of electron or they can share a pair of electron. What's the purpose of gaining a pair of electron or sharing a pair of electron? Simply to get extra stability or the electronic configuration of noble gases, which we call as a octet rule. Octet rule meaning when a bond is formed, both the non-metals, they have 8 electrons in the valence shell. Okay, I will show you how to draw a dot and cross structure of a covalent bond. Okay, but how a covalent bond is formed? A covalent bond is formed between two non-metals by simple sharing a pair, mutual sharing a pair of electron. Okay, you know, I want to explain a bit in detail. You know, they have shells. Atom or any element, they have shells. Like, for example, I want to take the easy one, hydrogen. Hydrogen has 1 electron in its outer shell. This hydrogen has also 1 electron in its outer shell. Hydrogen atom has shells. What's the electronic configuration? 1s1. I will teach you how to write the electronic configuration of all the metals in the periodic table in my separate video. Don't worry about it. For time being, ignore it. this hydrogen has one electron in its outer shell, and this hydrogen has also one electron in its outer shell. This one means it has one shell, it has one subshell, and it has one orbital, which is s orbital. This hydrogen also, it has one shell, one subshell, and it has one orbital, which is s orbital. So they come close together, and s orbital of this hydrogen and s orbital of that hydrogen overlap with each other and form a bond, which is called a covalent bond. Look at that. They form a covalent bond by overlapping atomic orbital. This bond, it's not a strong bond compared to ionic bond, because this bond is formed by simple overlapping a pair of overlapping atomic orbital. Okay. Anyway, covalent bond is formed between two non-metal by mutual sharing a pair of electrons. Covalent bond has direction, guys. Ionic bond has no direction. Ionic bond is non-directional. I have already explained in my previous video. Meaning it will not give you any shape. Like we are not writing NaCl like this. But covalent bond give you a proper shape. With the help of the covalent bond, you can figure out the shape of the molecule or the geometry of the molecule. I will teach you in my next video. Okay, now covalent bond can be a single covalent bond, can be a double covalent bond, or a triple covalent bond. Now I will give you the example of a double covalent bond. This is a single covalent bond. Sir, you told me they have 8 electrons in the outermost shell, but look at the hydrogen, it has only 2. Yes, hydrogen when it make a molecule, it will get the stability by having 2 electrons in the outermost shell. It can't share 8. It can't share. Hydrogen has no ability to share 7 electrons. It can only share 1 because it need 1 more. They get the electronic configuration of helium. Helium has 2 electrons in the outermost shell. So hydrogen molecule get the electronic configuration of helium. That's the duplex electronic configuration. Except hydrogen, except helium. When you look at the element in the elements of the group 7, except hydrogen, except helium, the remaining elements have 8 electrons in the outermost shell, guys. Look, helium 2, neon 10, 2, 8, argon 18, again 8, krypton 36, again 8, like that. All these elements, they have 8 electrons in the outermost shell. 1854, xenon 54, xenon 54, radon 32, 86. They have 8 electrons except helium. All they have 8 electron in the valence shell and the outermost shell. Now, example of a molecule having double bond. Can you give me the example of a molecule which is formed by 2 non-metals having double bond? Or double bond means they share 2 pairs of electrons. Let's see. They can form double bond, they can form triple bond. I didn't see the example they can share 4 pair of electrons. 3 only. So they can form triple covalent bond, a double covalent bond. Let's see the example of a double covalent bond. Can you give me the example of a compound having a double bond? Now, anyone, guys? A molecule or a compound having a double covalent bond. Oxygen atom. Look at the oxygen atom. This oxygen has how many electrons in the outer shell? 6. 1, 2, 3, 4, 5, 6. To get 8, they need 2 more. One more oxygen atom. It has also 6 electrons. Dot. 1, 2, 3, 4, 5, 6. They share. It's not complete transfer. Some students draw like this. It's not a complete transfer. They share it. They share 2 electrons each. 1, 2, 1, 2 remaining. It has 4 remaining. 1, 2, 3, 4. It has 4 remaining. 1, 2, 3, 4. Look how many electrons are there after sharing to each oxygen atom. 1, 2, 3, 4, 5, 6, 7, 8. That's the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. So it forms a double covalent bond. This is a double covalent bond or a double bond. So in case of the double bond, what we call a single bond and what we call this bond? Any idea? A single bond is also called as sigma. S-I-G-M-A, sigma bond. That's a new term, guys, I know. What about the double bond? Double bond is called a pi bond. I will teach you like a small asterisk, and that I will teach you how a sigma bond is formed and how a double bond is formed. Now look at that. My bad. How a sigma bond is formed and how a pi bond is formed. I will teach you. Okay. This is the example of a molecule having double covalent bond. Now, can you give me the example of a molecule having a triple covalent bond? Any idea? Think over it. Which element need 3 electrons to share it? Any idea? Any guesses? Good. Nitrogen molecule. Very good. Nitrogen molecule. Nitrogen need 3 electrons. So nitrogen and nitrogen, they form a triple covalent bond. Nitrogen atom and a nitrogen atom both share 3 electrons, 3 pairs of electrons. 3 electrons from each nitrogen atom. Look at the 3 electron. Triple covalent bond. Nitrogen has 5 in the outer shell. 1, 2, 3, 4, 5. This nitrogen also has 5 electrons in the outer shell. 1, 2, 3, 4, 5. They share. So that they will get 8 electrons in the outermost shell. They come close together. Each nitrogen atomic orbital overlap with the another nitrogen atomic orbital. Okay. To form a triple covalent bond, nitrogen, nitrogen, 1, 2, 3, 4, 5, 6, and it has 2 crosses and it has 2 dots. So nitrogen, check 1, 2, 3, 4, 5, 6, 7, 8. Yes, this nitrogen has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen also has 8 electrons. Nitrogen like this. 1 sigma pi a pi. And what we call these 2 electrons which are not participating in sharing. Any idea what we call these 2 electrons? These 2 electrons are called lone pair of electrons. You know, in the examination, if they will ask you to draw the molecule of nitrogen, you have to represent this lone pair in the form of orbital like, meaning these two electrons present in the orbital. So what is meant by the term orbital? Any idea? Orbital. Any idea? Define, or what is meant by the term orbital? We have orbit and orbital. Orbital is the space or the region where the electrons are present. GCSE 1 mark question, sometime A level. What is meant by the term orbital? It is a space near the nucleus where the electrons are present. Now, a lone pair of electron, 3 bonded pair of electron, 1 sigma bond, 2 pi bond. Now, after that, the important aspects of chemical bonding is the properties of the covalent bonding. We will do the properties of the covalent bonding. Before that, I will teach you the dot and cross structure of some of the compounds having covalent bond. Let's draw the dot and cross structure of covalent compounds. Okay. This is the example of dot and cross structure of covalent molecule. Let's do some compounds. Can you give me the example of a compound which has more than 2 nonmetals? Anyone, guys? You know that. Water, yes. Oxygen is a nonmetal and hydrogen also is a nonmetal. So draw the dot and cross structure of water, then ammonia, then methane. Okay, we will discuss. Dot and cross structure of water molecule H2O. Oxygen has how many electrons in the outermost shell, guys? Just now we did it. 6. Oxygen is 6 group element, meaning it has 6 valence electron. 1, 2, 3, 4, 5, 6. Hydrogen need just 1. Oxygen need, this oxygen need 2 more, and each hydrogen need 1. So hydrogen has 1 electron in the outermost shell. This hydrogen also 1 electron in the outermost shell. Dot dot. This hydrogen share with the oxygen. This hydrogen share with the oxygen. So that's the dot and cross structure of water molecule. Oxygen. This is the hydrogen, and this is also hydrogen. Hydrogen. Hydrogen dot and cross. Now oxygen has 1, 2, 3, 4 left. Look at that. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8, and hydrogen has 2, 2, because hydrogen just share 1 electron. Okay, that's the dot and cross structure of water molecule. Now, dot and cross structure of ammonia. Ammonia. Then I will teach you the geometry of water molecule, geometry of ammonia in my next video. Now draw the dot and cross structure of NH3, ammonia. Ammonia molecule. Okay. We know that nitrogen has 5 valence electron because nitrogen is coming from group 5. Okay, do you want to try it? Yep. Okay. Dot and cross structure of ammonia molecule. Then we will do methane. Ammonia. Okay. Nitrogen has how many electrons in the valence shell? It has 5 electrons in the valence shell. Nitrogen 1, 2, nitrogen 1 2 1 2 1 2 3 3 hydrogen. Hydrogen has only one and 1 here. They share each other. Look at that. So that's the central atom, nitrogen, which is only one atom. That's called central atom, and it has surrounded by 3 hydrogen. 1 hydrogen, a 2 hydrogen, and this one also hydrogen, and lone pair. Ammonia has 1 lone pair. So how the structure represent? I will teach you. So this is NH3 with a lone pair. I will teach you the perfect geometry of ammonia molecule in my future videos. Now, you want to try methane? So all are single bond, guys. No double bond. Ammonia has no double bond. 3 bonded pair of electron and 1 lone pair. No double bond. You will try methane. You want to try methane? So carbon and carbon Neet. Let's see. Draw the dot and cross structure of methane molecule. CH4 methane. CH4 dot and cross structure of methane. And you know that why the formula is CH4? Because carbon need 4 more electron to complete its valency. That's why it's shared 4 more electron from 4 hydrogen atom. And you can say why the ammonia has NH3, because a nitrogen need 3 more electron. In the same way, carbon need 4 more electron to complete its octet configuration, to complete its full electronic configuration. Carbon has how many in the valence shell? 4. Carbon has 4. Look at that. Carbon has 4. Carbon is from group 4, so it has 4 electron in the valence shell. 1, 2, 3, 4. So 4 hydrogen. Hydrogen can share only 1. 1 hydrogen dot. Dot, guys. This is dot. 2 hydrogen dot. There is no fixed rule that you have to always show the central atom, which is a single atom with the cross electron, and all the surrounded atom with the dot electron. No, you can swap it. You can shift it. You can draw cross here and dot here. There's no rule that we have to draw cross only for central atom. Now, it's just a kind of representation, guys. This 2 dot and cross shows this electron from carbon and the electron from hydrogen. It's just a type of representation. This is also a dot, this hydrogen, and this hydrogen also has 1 dot. So they overlap, all these atomic orbital overlap to form a molecular orbital and form 4 covalent bond. 1 hydrogen, 2 hydrogen, 3 hydrogen, 4 hydrogen, a dot and a cross, a dot, cross and a dot, a cross and a dot, cross dot, hydrogen, 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 hydrogen. You want to try PCl5? Yep, dot and cross structure of PCl5. We believe that almost all the covalent compounds follow the octet rule. An octet rule tells you the stability of the compound or the molecule, but certain molecule in the periodic table or certain compounds form due to the covalent bonding will not follow the octet rule. We will do this example. They do not have 8 electrons after overlapping. One of the example is the PCl5. PCl5 has no 8 electron in the outermost shell even though it is the stable compound BF3 PCl5. Check, 8 electron in the outermost shell. Yes, 100% stable because 8 electron. But try the PCl5. Can I give you the example PCl5 as homework? Do you want to try PCl5? Okay. Yep. Draw the dot and cross structure of PCl5, phosphorus pentachloride. Oh, bad smell, man. Like fishy smell. Very bad smell. Okay, guys, I want to stop my video here and I will come back soon with more example of dot and cross structure like ethene. Best example, I've seen that one in many past paper. Ethene, carbon dioxide, and what else? BF3 PCl5. We will continue in my next video about the dot and cross structure of those molecules. Thanks for watching this video, guys. Hi guys, welcome back to my channel. How are you guys? I'm hoping for your good health. So see that, look at that question. We will discuss this question first before I proceed further for the chemical and physical properties of covalent compound. Now, I have taken this question from the OCR textbook and I've seen one of the past paper that question appeared, like draw a dot and cross structure of ethene molecule. That's why I have taken this question. Okay, do you want to try it? Fluorine molecule, easy though. Fluorine has how many electrons in the outer shell? 7. Fluorine is from group 7 element. Dot 1, 2, 3, 4, 5, 6, 7, and one more fluorine, which has 7 electrons. 1, 2, 3, 4, 5, 6, 7. After sharing, they have 8 electrons in the common shell. Okay, and we know that a covalent bond is formed between two nonmetals. If suppose they will ask you what type of chemical bond is present in any of the following compound, they will give you draw a dot and cross structure of ethene and mention the type of bonding present in ethene. So ethene is a compound having carbon and hydrogen. So what type of chemical bond is present? Obviously covalent. Okay, now hydrogen fluoride, fluorine molecule, hydrogen fluoride, HF. Hydrogen has how many electrons in the outermost shell? 1. And just now we have done fluorine. Fluorine has 7. 1, 2, 3, 4, 5, 6, and 1, 7. HF. Easy. Dot and cross structure is very easy, guys. And these remaining pair of electrons are called lone pair. Now, SiF4. I have shown in my videos methane molecule. So SiF4 is similar to methane molecule. Silicon tetrafluoride. Can I rub the board here? If you don't mind, can I rub the board, guys? Okay. Silicon is from group 4. So having how many electron in the outermost shell? Has 4 electron in the outermost shell. Look at that. Silicon has 4 electron in the outermost shell. Si from group 4 has 4 electron in the outermost shell. 1, 2, 3, 4, and all are shared with 4 fluorine. 1, 2, 3, and 4 fluorine. Fluorine has how many? 1 and 7 remaining. 1, 2, 3, 4, 5, 6, 7. 7, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. This is the dot and cross structure of SiF4. Now, sulfur dichloride, SCl2. Sulfur dichloride. Check. Sulfur is from group 6. What does it mean? It has 6 electrons in its valence shell. So draw 6 electrons for sulfur. Sulfur is the central atom for SCl2. Silicon is the central atom for SF4. Central atom is the main atom around which some non-metals are grouped to form covalent compounds. Why I'm stressing central atom? When I will teach you how to draw the shape of the molecule or how to predict the bond angle of the molecule, that will be very important. We have to discuss in terms of central atom. So the bond angle we will discuss in terms of central atom. Okay. Now CCl2. Sulfur has how many in the outermost shell? 6. 1, 2, 3, 4, 5, 6. And chlorine need only 1 to get 8 electron. So 1 chlorine. Chlorine has 7. 1, 2, sorry, dot cross. 3, 4, 5, 6, 7. So this chlorine 1, 2, 3, 4, 5, 6, 7, 8. Outermost shell is completely filled. One more chlorine. 1, 2, 3, 4, 5, 6, 7. This chlorine has 8 electron after sharing. Sulfur has 8 electron after sharing. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, carbon disulfide, like carbon dioxide. This structure is very similar to carbon dioxide. So I'm doing for that. You will try for carbon dioxide. Okay. Look at that. Carbon is the central atom for carbon disulfide, like oxide. This is sulfide. Any non-metal we named as ide when they form compound. There's a difference between ite and ate. I will teach you ite and ate. Or you can watch my videos on titration. I have already explained the difference between ITE and ATE or IDE. Now, carbon has how many in the outermost shell? 4. 1, 2, 3, 4. Sulfur need how many, guys? How many electron to get 8 electron in the outermost shell, or to get full outermost electronic configuration? Sulfur need 2. So look at that. Sulfur and carbon always make a double bond because sulfur need 2 electron. Sulfur has how many? 6. 1, 2, 3, 4, 5, and 6. Double bond. 6 group and 4 group, always there will be one double bond. And this also, again, sulfur need 2 electron. 2 electrons shared by carbon and 2 electrons shared by sulfur. So there will be one more double bond. Here is a double bond. Sulfur 1, 2, 3, 4, 5, 6. Look at the structure. This is like this. No, it's not a bend, it's linear. I will teach you the shape of the molecule, don't worry. Carbon, double bond S, double bond S. Single bond is called sigma bond, and a double bond is called pi bond. So sigma, sigma, pi, pi. Sorry, guys. Ethene. I've seen this question in the past paper. Ethene, carbon and hydrogen. Ethene is an example of hydrocarbon. Hydrocarbon contain carbon and hydrogen molecule. and they bonded each other by means of a covalent bond. Okay, hydrocarbon, no worries, I will teach you later on. Hydrocarbon, ethene molecule, C2H4, ethene, C2H4, ethene. Ethene is a gas, ethene molecule, ethene. Carbon, look at carbon, and we know the carbon has how many electrons in the outermost shell? 1, 2, 3, 4, and 2 carbon. Sorry, I want to draw the 2 carbon. I need a bigger space. 2 carbon. Look at the 2 carbon. This is a carbon. First, we will do bonding between carbon and carbon. Then I will show the sharing between carbon and hydrogen. This carbon has 2 electrons in the outermost shell. This carbon also has 2 electrons in the outermost shell. 1 and a 2. 1 dot 1 cross this carbon. Now, each carbon has 2 more electrons left. This carbon has 1 electron left, 1 electron left. This carbon has dot and a dot, 2 electrons left. So this carbon share with 1 electron with 1 hydrogen. Hydrogen can only share 1 electron with this hydrogen. But this carbon also share 1 electron with the hydrogen and 1 more electron with this hydrogen. Look at this molecule. Quite interesting molecule. I will draw how it looks. Carbon, carbon, and a carbon, double bond, 2 hydrogen, single bond, and a single bond. This is also a single bond. This is a single bond. Sigma, 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 pi. Okay. Carbon dioxide and sulfur dioxide, same. I'm not doing carbon dioxide. You will try it. Now, hydrogen cyanide, HCN. Now, okay, can I rub the board, guys? HCN, hydrogen cyanide. Hydrogen is a non-metal, carbon is a non-metal, and nitrogen is a non-metal. They all 3 combine to form HCN, hydrogen cyanide. Okay. Let's focus on carbon. Carbon has how many electrons in the outermost shell? 4. This carbon share 1 electron with hydrogen because hydrogen can share only 1. How many electrons left with this carbon, guys? 3 electrons. Look at that. 3 electrons. 1 dot, 1 cross, 1 more cross, 1 more cross. Okay. Nitrogen is from group 5. Group 5 meaning nitrogen has 5 valence electrons. To get full outer shell electronic configuration, it share with 3 more electrons. So this nitrogen share 3 electrons from carbon. So big nitrogen molecule here, and it share how many electrons? 1, 2, 3. And nitrogen has 1 lone pair. This is the lone pair of the electron. So hydrogen, a single bond with carbon, a triple bond with nitrogen. This is the structure. I will teach you the bond angle and the shape. Don't worry about the bond angle and the shape. Okay, we have done this question nicely. Now, physical properties and some chemical properties of the covalent compounds. Okay. Properties of the covalent bonded compounds or covalent compounds. Properties of covalent compounds. Since covalent bond is formed by sharing a pair of electrons, it is not a strong bond. It is a weak bond compared to ionic bond. The force of attraction is very weak. What type of force of attraction? A wonderful, a wonderful type of force of attraction. Based on the force of attraction, I will make a separate video. Don't worry about it. Well, it's a weak force of attraction between the atoms of non-metal. Compared to ionic bond, there's a weak force of attraction. So we would expect less melting point and a boiling point. And one more thing, guys, keep in your mind that here, here I'm discussing simple covalent compounds. I will teach you giant or macro covalent compound later on, which is slightly different from simple covalent compound. Okay, so I'm keep on telling. So keep in your mind that here we are doing only simple covalent compounds, not the macro covalent compound or not the macromolecules. Now, properties of simple covalent compounds. Properties of simple molecules or simple covalent compounds. Covalent compounds, like just now explained, it is formed by sharing a pair of electrons, so they have less melting point and a boiling point. Important property, they have less melting point and a boiling point. Less melting point, less melting point and a boiling point. And can I write simply BP? That's boiling point. Yep. Now, solubility. In general, I'm not talking about the polar and non-polar. In general, they are not soluble in water molecule. They are insoluble in water molecule. We will discuss polar and non-polar later on. So they are so the polar covalent compound soluble in water. I do agree. I'm coming to the point of polar and non-polar covalent compounds later on. They are they are insoluble. That's the journal trend. That's the journal property. They are insoluble in polar solvent, or you can say water molecule. They are insoluble in water molecule. They're insoluble in water, and they do not conduct electricity. They do not conduct electricity because there is no movement of electron. In case of ionic compound, there will be a movement of ions. Free ions we have seen in case of aqueous solution and molten solution. Here there is no free electrons. So they are bad conductors of electricity. Except one compound. I told you I will teach macromolecule. Can you give me the example of one of the macromolecule which conduct electricity? Any idea? It is a form of carbon. Graphite. Graphite is a macromolecule which conduct electricity, and because of a delocalized electron. So when they will ask you why the ionic compound conduct electricity, your answer will be due to the movement of free ions. Don't use the term delocalized electron. Most of my students, Delocalized electron you have to use in terms of graphite or metallic compounds. Metallic compounds, they conduct the electricity because of the presence of delocalized electron, and graphite also because of the presence of delocalized electron. Okay, but in general they will not conduct electricity. They are the bad conductors of electricity except graphite. Okay guys, these are the some physical properties of covalent compounds. Yeah, that's the general properties. We will discuss later on. Because of the presence of hydrogen bonding, they are dissolved in water. That's a different case. But in general, they have less melting and boiling point. They are insoluble in polar solvent. Example like water. They are bad conductors of electricity. Now, okay. Now, covalent compounds. They are of two types: polar covalent compounds, and non-polar covalent compounds. Non-polar covalent compounds. Okay, best example, water molecule. This is benzene molecule. Okay, guys, thanks for watching this video. I want to stop this video and I will continue the difference between the polar and non-polar covalent compound. Why this compound, suppose like I said to you, water is a polar molecule. Why water is a polar molecule? And I gave you the example of benzene. Why benzene is non-polar? We will discuss this one. Okay guys, thanks for watching this video. Hi guys, welcome back to my channel. So what's going on guys? You know that to make all these videos, I'm putting my 100% effort. So what's your job? Your job is to watch my videos continuously. Definitely, all my videos will boost your knowledge of chemistry, and you can easily get good grade in your final examination. Maybe A or maybe B, but you have to watch my videos constantly. Don't miss my videos. Okay then, see. Today I'm going to teach you polar covalent bond and non-polar covalent bond. I've already started in my previous video about covalent bonding. Now, why some covalent compounds are polar and some are non-polar? What's the condition that makes the molecule polar and makes the molecule non-polar? Let's see. To discuss about the polarity of the covalent compound, we have to know a small parameter or small unit called electronegativity. Electronegativity is not the energy. Some student getting confused with ionization energy and electron affinity. Ionization energy and electron affinity, these are energy values. Electronegativity is not the energy value, it's the ability of a non-metal in the periodic table. When two non-metal join to form a covalent bond, one of the non-metal has more ability to attract the shared pair of electron. That's called electronegativity. Now, first, let's see what is meant by the term electronegativity. Electronegativity. Okay, electronegativity is the tendency, or it is the ability. It is a It is a tendency. It is a tendency to attract the shade pair of electrons when bonded covalently. So when a covalent bond is formed, one of the element has the ability to attract the shade pair of electron. So we didn't get it. Okay. Look at the HCl, hydrogen and chlorine. That's the HCl molecule. So dot and cross structure of HCl. Hydrogen has 1 electron, chlorine has 7. 1, 2, 3, 4, 5, 6, 7. This is hydrogen and this chlorine. Mostly the bond is present between the two elements. That's the nucleus and that's the nucleus. This is the nuclear distance and the lone pair of the electron, bonded pair of the electron in between the two nucleuses. But because of the electronegativity power of the chlorine, the two electrons slightly shift towards the chlorine. Look at that. That two electron move towards the chlorine. This is the ability of the chlorine that will attract the shade pair of the electron. As a result, this hydrogen get a slight positive charge and this chlorine get a slight negative charge. This is called partial positive. This is called partial negative. We can't call them as complete. We can't call them as ions, but the distribution of charge take place, which we call as dipole. I will teach you dipole later on. Okay, so some element in the periodic table has more ability to take or to withdraw this pair of electron towards itself. That phenomenon is called electronegativity. Okay, guys. So is the tendency or is the ability? It's just a 1 mark question. What is meant by the term electronegativity? Okay. Presence of electronegativity make the molecule polar. Okay. So polar molecule. Now, electronegativity increases across the period and decreases down the group. En value, electronegativity, I'm writing just En, which is a short form of electronegativity. Electronegativity value increases across the period and decreases down the group. And electronegativity is the property of non-metal, guys. It's not the property of the metals. It's the property of non-metal. Now, look at that. Nitrogen, fluorine, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So electronegativity value increases like this and decreases down the group. Look at the electronegativity increases across the period, decreases down the group. So nitrogen, when you move from nitrogen to fluorine, electronegativity increases. Electronegativity value increases across the period and decreases down the group. Look. So when you move from nitrogen to fluorine, electronegativity value increases and electronegativity value decreases down the group, guys. So the highest electronegative value is 4, and which element has the highest electronegative value? Fluorine. Electronegativity value is measured by Pauling scale. It has no unit because it's a tendency. So electronegativity has no unit. It's just a value. It's just a number. Fluorine has the highest En value, which is 4. Fluorine has 4. That's the electronegativity value. See, the phenomenon electronegativity makes the molecule polar. If there will be a difference in the electronegativity, then the molecule or the compound has partial positive charge and partial negative charge. Look at the example. Yeah, look at that example. Look at that one. So, like hydrogen chloride, we have seen just hydrochloric acid or HF, HCl, no HF. Hydrogen and fluorine, hydrogen fluoride, hydrogen and fluoride. Fluorine has the highest electronegativity, so it withdraw or attract the shade pair of electron. So that shade pair of electron moves slightly towards fluorine. As a result, fluorine got slight negative or partial negative charge, and hydrogen got a partial positive charge. This makes the molecule polar. More the electronegativity value, or bigger the difference between the electronegativity value of hydrogen and fluorine, makes the molecule slightly ionic. I told you that no covalent compound is 100% covalent, or no ionic compound is 100% ionic. Ionic compounds have certain percentage of covalent character. In the same way, covalent compounds also, they have the percentage of ionic character. Because of the electronegativity differences, they have partial positive charge and a partial negative charge, which makes the molecule slightly ionic. That's why they are dissolved or they are soluble in polar solvent, like water. HF is soluble in water because it is polar. You can easily notice ions are formed, no doubt partial ions, not complete ions, partial. So it will dissolve in water. On the other hand, look at the non-polar molecule. So how can we check the non-polar compound? If the electronegativity difference is 0, look at that. If delta En, what's delta En? Electronegativity value is equals to 0. Here, if delta En, difference in electronegativity, is not equals to 0, fluorine and hydrogen, there will be a difference in electronegativity value. Can you give me the example of non-polar molecule? Any non-polar molecule? Hydrogen and hydrogen. Hydrogen and hydrogen. Both these two are hydrogen, so they do not have ability to attract the shade pair of electron. So this bonded pair of electron is exactly lies between two hydrogen atoms. So this is the hydrogen atom. This is the hydrogen atom. This is called the nuclear distances. So that's the nucleus, that's the nucleus. So exactly the bonded pair of electron lies here. Because the electronegativity difference is equals to 0, which makes the molecule non-polar. We have some other example of non-polar molecule. So non-polar molecule will not dissolve in polar solvent because we cannot find any charge separation. Here, look at that. Here there is a charge separation or charge distribution. This charge distribution, we call it as dipole moment. There is a partial positive and partial negative charges. So this is also called charge separation and a dipole. Dipole means on the molecule or on the compound we have positive end and a negative end. That's called dipole. There is no dipole here. Okay. Now one more example of non-polar compound. Non-polar. So many examples. How can we know? Means what's the condition for non-polar compound? Electronegativity difference is equals to 0. That's the main condition. Now, Some more molecules of non-polar compounds? Yes. Any idea, guys? Do you want to give me some example of non-polar? Chlorine, chlorine molecule, bromine molecule, iodine molecule. Two same atom. Obviously, there's no difference in electronegativity. So all of these molecules are non-polar because the electronegativity difference, the delta En value is equals to 0. Look at that. Delta En is equals to 0. And a non-polar. This is non-polar and polar. HF, HCl, HBr, HI. All are polar. Polar covalent compound. Polar covalent compounds, they are dissolved in water. They are soluble, not 100% soluble, but they are soluble. When you compare polar covalent compound and ionic compound, which one are more soluble in water? Ionic compounds. Because in case of ionic compound, we will get separate ions like Na plus and Cl minus. Here we are not getting H plus separate and F minus separate. No, there is a charge distribution which makes the molecule slightly ionic. That's why they dissolve in polar solvent. They are soluble in polar solvent. Like water is a good polar solvent, ammonia. They are soluble in polar solvent. Now, look at the HCl, HBr, HI, all are polar. Now, this charge distribution is also called dipole. Let's do some discussion of dipole moment. Okay, now the dipole moment. Do we have a dipole moment in non-polar compounds? No dipole moment. There is no charge separation. But here we have a charge separation. Now the dipole moment. Dipole moment. Dipole moment, how we measure? It is the distance between, like for example, hydrogen and fluorine, hydrogen fluoride. It is the distance. Suppose this is the hydrogen molecule, this is the hydrogen atom, this is the fluorine atom. Here we have hydrogen, here we have fluorine. This is called interatomic distances. Yeah. So dipole moment is the product of distance from here to here and the charge separation. This distance and the charge separation and the quantity of the charge, partial positive, partial negative. So is the product of quantity or magnitude of the charges and the interatomic distance. That will give you dipole moment. Dipole moment is a vector quantity. Any idea about the vector quantity, guys? I know, it's too much. Vector quantity is like a physical quantity, and the vector quantity has both a magnitude and a direction. And a scalar quantity has only magnitude. I will give you just a few examples of vector quantities and scalar quantity. Like time is a scalar quantity. It has no direction. And the volume is a scalar quantity. But look at the force, and we have a velocity. I'm not teaching physics, but I'm just telling you vector quantity. What is meant by the term vector? Vector quantity. Dipole moment is a vector quantity. It has direction as well as magnitude. See, it moved from partial positive to a negative. Like you have to show the arrow like this. So suppose this is HF, hydrogen fluoride, partial positive, partial negative. We have to show the movement like this, from positive end to negative end. This is called dipole moment. which is a vector quantity. So it has a direction and magnitude. Vector quantity is a quantity which has both the direction as well as magnitude. For example, velocity. Velocity is a vector quantity. It has a direction as well as magnitude. Acceleration is a vector quantity. Okay, now dipole moment. Dipole moment. So what is the importance of this? More the charge separation, more will be the polar bond. More will be the polar bond mean more percentage of ionic character. For example, hydrogen, chloride, HCl, partial positive, partial negative. So the dipole movement move from positive to the negative end. More the charge separation, more the value of dipole moment, more will be the charge separation, more will be the ionic character, more will be the polarity, and it is easily dissolved in polar solvent. Now, it is a vector quantity. We know that. It has a unit, guys. It has a unit. Dipole moment. That was a past paper question. Any idea what's the unit of dipole moment? Debye. D-E-B-Y-E. Debye is the unit of dipole moment. Now, I told you how can we check whether the molecule or the compound is polar or non-polar. The first condition is difference of electronegativity. First, what's the main condition? How can we check difference in electronegativity? En value different. If the En value is not equals to 0, simply molecules are compound, molecules are said to be polar. If difference in electronegativity is equals to 0, like chlorine molecule, iodine molecule, bromine molecule, then the molecule is said to be non-polar. Molecules are said to be non-polar. Suppose I'm giving you one example of BF3. BF3 is a polar or non-polar. Then how can we decide? By using this criteria or some other criteria. Okay, let's check. Mostly this happen in two similar atoms. If suppose we do not have two similar atoms, then how can we check the polarity of the molecule? We have one more condition called dipole moment. We have to focus on dipole moment, which is a vector quantity. Look at that one. Check whether the BF3 is polar or non-polar. See, it's a polar molecule or non-polar molecule. BF3, boron trifluoride, fluorine, a fluorine, and a fluorine. There is a difference in electronegativity, guys. Boron has different electronegative value and fluorine has different. So the condition, first condition, if delta En, difference in electronegativity, is not equals to 0, then the molecule is said to be polar. But that's not right. This only applicable for the molecule of same atom. Now, how can we decide this molecule is polar or non-polar? We will draw its dipole. So we know partial positive, partial negative, partial negative, partial negative. So this bond, this dipole goes in this direction, this dipole goes in this direction, and this dipole goes in this direction. If you're getting confused with dipole, you think this is a kind of force. So one force goes here, one force goes here, and one force goes here. You add up these two forces, that's the resultant of that one. This is one force going up, and this is one force going down. Both the forces cancel out. So there is no net dipole moment. If there is no net dipole moment, then the molecule is said to be non-polar. Past paper question: why ammonia is a polar molecule and a BF3 is a non-polar molecule? Look at that. So the reason behind is, no doubt, the difference in electronegativity value is there, but there is no net dipole. Best answer: there is no net dipole, or resultant dipole moment is cancelled off. Why BF3 is non-polar? Answer, simple answer: because there is no net dipole. I have seen the mark scheme, guys. In the mark scheme, it is mentioned as simply there is no net dipole. No net dipole, or dipole cancel out. Dipole moment. Dipole moment cancel off. Let's check the ammonia. Ammonia, nitrogen, and 3 hydrogen. Same thing. Instead of ammonia, take NF3, nitrogen trifluoride. NF3 is a polar, whereas BF3 is non-polar. That was a past paper question. Let's check the NF3. Why NF3 is polar? Okay. Why NF3 is polar? Nitrogen, fluorine, 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 and lone pair. Okay. This is the molecule of nitrogen trifluoride. Which one will become a partial positive? Fluorine has less electronegative. The electronegativity value of fluorine is more, nitrogen is less. So nitrogen got positive charge, a negative charge, a negative charge, a negative charge. So this goes here, this goes here, this goes here, and because of the lone pair, that goes up. So one like this like this, that's like this like this. So all cancel. No, we can't cancel. So these three in one direction, we can't cancel. Sorry, my bad. We can't cancel here. All three goes in one direction. Only one goes up. So these three in downward direction, and that's upward direction. So we cannot cancel. Why NF3 is a polar molecule? The reason behind is NF3 is a polar because there is a net dipole. The dipole cannot cancel here. There is net dipole. That's the reason. So I want to stop my video here. We will do some more questions based on dipole and how it is useful to figure out the polarity of the molecule. Please, I'm requesting you have to watch my videos. I know you're in summer break and you're not in a mood to study, but even though when you have a leisure time, when you're free, at least 30 minutes, guys. My videos are not more than 30 minutes, or my maximum video time is 30 to 40 minutes. Just utilize your time for 20 to 30 minutes and watch my videos. Thank you. Welcome back to my channel, guys. Today I'm teaching you dative covalent bond, which is a type of a covalent bond. Actually, this is an extension of a covalent bonding. Okay, let's see. First, a covalent bond is formed between two non-metals. We know that. And how it is formed, I have discussed this in my previous video. Anyone? How a covalent bond is formed? It is formed by simple sharing a pair of electrons between two non-metals. We can say a mutual sharing. So this is an extension of a dative covalent. This is an extension of a covalent bond. Okay, first of all, see what is meant by the term dative covalent bond. See, dative covalent bond, which is also called as a coordinate covalent bond. It is a type of covalent bond. It is a type of covalent bond in which shared pair of electrons are provided by one of bonded atoms only. So we didn't get it. In case of the covalent bond, sharing of an electron takes place between two nonmetal. It is a type of the covalent bond in which the shared pair of the electron provided by only one atom having lone pair. Lone pair of electron which do not participate in chemical bonding. That will help to make a dative bond. Okay, guys. Let's see some example of dative covalent bond. We have two examples: hydronium ion and ammonium ion. Let's do the first example of ammonium ion. How a dative covalent bond written? Look, A arrow B. It means A having a covalent bond with B and donate a pair of electron to B. B, after making a covalent bond, A is left with lone pair of the electron and A donated a pair of electron to B. Here B is electron deficient. This arrow represents movement of electron or donation of electron from A to B. A donate a pair of electron to B. Okay, A contains lone pair of electron. Look at the example of ammonia and ammonium ion. Look at that one. Ammonia, you know that ammonia is a covalent compound because nitrogen has 3 electron share with 3 hydrogen atom and nitrogen left with a pair of electron. Okay. When an acid dissolves in water, it gives away H plus ion. This is the property of an acid. So all the acids which gives away H plus ion, that is proton, in water when dissolved in water. So we have H plus ion. This H plus ion has no electron. It has only one proton. Hydrogen has 1 electron and 1 proton, but that H plus ion has no electron, lost the electron. It gives away the electron. Now, nitrogen, after making 3 bonds, still has 5 electrons. It still has a lone pair left on the nitrogen. Nitrogen is from group 5 element. It can easily make 3 covalent bonds. Along with that, it has 1 lone pair left. That lone pair donated to H plus ion to make a dative bond. See how we write the dative bond? Look at that. Nitrogen already has 3 hydrogen atom and one more bond which is called a dative bond to the hydrogen atom. This hydrogen atom has no electron. That electron donated by nitrogen. So it is a one-side donation. In some books, it is written as back donation. So it is a type of back donation. So these two electrons come from nitrogen. It's a sharing, but sharing by only one of the bonded atoms. So look at that. I missed something. Look at that. What I miss? Any guesses? Nitrogen can make 1, 2, 3 bond. Here nitrogen made 4 bond. 1, 2, 3, 4. Nitrogen has trivalent. It can make only 3 bond. If it is giving away a pair of electrons to make a dative bond, we have to write a positive charge, overall positive charge on the nitrogen, because nitrogen lost a pair of electrons towards hydrogen, and this is called ammonium ion. When we have a suffix called em, meaning a positive charge ion, ammonium. So I've seen many past paper questions in that they ask draw a dot and cross structure of ammonium ion. So ammonium, in case of ammonium ion, nitrogen make a dative bond with H plus ion. Look at that one more example. First, I want to draw the dot and cross structure of ammonium ion. Okay, this arrow show donation of electron from nitrogen to hydrogen. I will give you one more example, like hydronium ion. Let's draw the dot and cross structure of ammonium ion. 2 mark, or I never see 3 marker in that, mostly 1 mark. Or if they will ask draw a dot and cross structure of ammonium ion, that could be a 3 marker. Dot and cross structure of ammonium ion, NH4 plus. Like, first start with the ammonia, dot and cross structure of ammonia. Central atom is nitrogen. Nitrogen has 1 electron, 1 electron, and 1 electron. Each share 1 electron with hydrogen. That's from the hydrogen. 1 electron and electron from the hydrogen, 1 electron and 1 electron from the hydrogen. Nitrogen has 2 electrons which are shared with hydrogen atom. So this is a dot and cross structure of ammonium ion. You have to focus on these 2 dots. These 2 dots mean that 2 electron donated by nitrogen. One more example of hydronium ion. Hydronium ion. Whenever we end up with em, like a suffix em, meaning a positive ion, and they have a dative bond. Just now I told you, acid when dissolved in water, it gives away H plus ion. Any acid like HCl, HNO3, nitric acid, sulfuric acid, all the acids, hydrochloric acid, nitric acid or nitric acid, sulfuric acid, all these acids, when dissolved in water, it gives away H plus ion. So that H plus ion comes from acid, and this H plus ion has no electron. Now look at the water, like we have H2O, 2 electron with nitrogen, oxygen has, let me draw in different way, like this is oxygen, 1 electron with hydrogen, 1 electron with hydrogen. So this is hydrogen, this is oxygen. So oxygen has total 6 electron, 1 electron and share with hydrogen, 1 electron and 1 share with hydrogen. It left with lone pair. That lone pair take part in making a dative bond. Not both the lone pair, just one lone pair, guys. We do not have like H4O. That's not possible. We have H2O and two lone pair. Either of that lone pair donated to H plus to make a dative bond. Now, oxygen donated a pair of electrons to this hydrogen and form a dative bond and make a dative bond. Look at that. Look at the dative bond. Oxygen, one hydrogen here, normal covalent bond, one more hydrogen. This hydrogen has a positive charge before that, and now it gained two electrons from this oxygen. Always positive ion, we have to put a plus charge here. So this arrow represents a dative bond, and the head shows you a pair of electrons donated by oxygen. So that's the direction, oxygen to hydrogen. What's the name of this ion? Hydronium. Hydronium ion. Okay. Now that's the let's draw the dot and cross structure of hydronium ion, which is easy. Before that, it has two covalent bonds. Oxygen atom has one covalent with hydrogen, one covalent with one more hydrogen. Here, I want to draw here. This oxygen, one covalent with hydrogen, one more covalent with hydrogen, 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 a covalent bond, one more covalent bond, and a dative bond. Dative bonding, this dative bond, a bond shared formed by a shared pair of electrons only from oxygen. This is the oxygen. When we deal with the transition metal form complexes. I will teach you in my future videos. In complexes, normally central metal atom come from transition element like iron, copper, anything like all the most of the d block element. They form the complexes. In case of the complexes, the ligand donate a pair of electrons to central metal cation, which is a transition metal, and they also form a dative bond. That's the dative bond. Dative bond, it's a kind of back donation, or it's a type of a covalent bond in which one of the bonded atoms donating shared pair of electrons. Okay, guys. Can we do one question? Okay. I will give you one example. You have to predict the bonding present in that compound. See, mostly dative covalent compounds form ionic bonding. Quite surprising, yes, because they form ions, hydronium ion, ammonium ion, and they also participating in making ionic bond. Let's do one question, guys. Predict the type of chemical bond present in ammonium chloride. Any guesses? First, let's start with ammonia. Ammonia, NH3, covalent. Ammonia make ammonium ion. Just now we have done with the help of a dative bond. This is dative or coordinate covalent. Ammonium ion NH4 plus. The plus charge is not on the hydrogen, it's overall. Combine with Cl minus and make ammonium chloride, which has ionic bonding. So it has all three, guys. I like this example. This example has all the three different types of bonding: covalent, dative, and ionic. And the last type of bonding is metallic. I will teach you the metallic bonding. I know that. I will make a video on the metallic bonding. After that, I'm going to start shape of the molecules, or I'm thinking either the shape of the molecule or the intermolecular force of attraction. That's hydrogen bonding, permanent dipole, or induced dipole. Okay, guys. Thanks for watching. Hi, guys. How are you guys? Welcome back to my channel. Let's start today's topic. Today I'm going to teach you intermolecular force of attraction. Look at that. We have different types of intermolecular force of attraction. Among them, one is hydrogen bonding. Hydrogen bonding. We have permanent dipole interaction. It's called PD. And we have induced dipole, which is also called as one Waals force of attraction. Hydrogen bonding, permanent dipole. Permanent dipole interaction. Dipole interaction. Last one, induced dipole interaction. It's called ID, dipole interaction. We have PD, that's the way of writing PD, that's ID, which is also called as van der Waals force of attraction. Some books it's called London forces. It is mentioned as London forces. Van der Waals force of attraction. And London force. Let's start the hydrogen bonding. My today's topic is hydrogen bonding. Let's see the hydrogen bonding first. Okay. Can I rub the board? Okay. Look at that. Hydrogen bonding. First of all, let's see what is meant by the term hydrogen bonding. Intermolecular force of attraction. It's not an actual bond. It's an attraction between the two molecules. First of all, we have covalently bonded molecules. Among the covalently bonded molecules, we have these type of attraction. Inter mean in between two molecules, guys, in between two compounds. We have intra also. Intra is ionic bond, covalent bond, dative bond, metallic bond. Now, hydrogen bonding. Let's see the hydrogen bonding. Hydrogen bonding. It is a type of electrostatic force of attraction between positively charged hydrogen of one of the compound and a highly electronegative atom of another molecule. Okay, so it is a electrostatic force of attraction between positively charged H plus and of hydrogen of one compound of one molecule of one molecule and highly electronegative elements or atoms, highly electronegative elements of another compound or molecule. Hydrogen bond is present only between hydrogen and highly electronegative atoms, such as highly electronegative, instead of elements I want to write atoms, highly electronegative atoms such as fluorine, oxygen, nitrogen, phone, such as phone. So one of the molecule should have hydrogen and another molecule should have fluorine, or either fluorine or oxygen and nitrogen. And because of the presence of hydrogen bond, the properties of the compound or the molecule changes. Let's see. First of all, they will ask, draw a hydrogen bonding in between two water molecules, in between two ammonia molecules, or in between water and ammonia molecules. We will see that one. So it's a type of attraction, electrostatic attraction, between a positively charged hydrogen atom and highly electronegative atoms of another compound like FON, fluorine, oxygen and nitrogen. Electronegativity increases across the period. Most of the students ask me a question, HCl has hydrogen bonding? No, HCl has no hydrogen bonding. HCl, hydrogen with fluorine, hydrogen with oxygen, hydrogen with nitrogen. Okay. Water has hydrogen bonding? Yes. HF, hydrogen bonding? Yes. Ammonia, hydrogen bonding? Yes. Now, so let's do some past paper question. Okay. Is that clear? Look at the question. Draw the hydrogen bonding between the two water molecules, between two ammonia molecules, and between water and ammonia molecule. Okay. This question could be a 3 marks question. Yep. Now let's see between the two water molecule. Hydrogen bonding between the two water molecule. Let's see between two water molecule. Just draw a water molecule close to each other, like that's the water molecule, which are close to each other. Oxygen and a 2 hydrogen covalently bonded. Another water molecule, that one and this one. Okay, which one is highly electronegative, guys? Oxygen is highly electronegative, so you have to put a partial, a slight negative charge, a slight positive charge, slight positive, partial negative, partial positive, partial positive. Do I need to put this one? Yes, it's compulsory to, you have to draw the dipole. Okay, now look at that, hydrogen and another oxygen molecule, or an oxygen and a hydrogen, either way is possible. So, and the hydrogen bond is represented by a dotted line. How? between one oxygen and a hydrogen. So this one, guys, this one is hydrogen bonding. Okay, that's the hydrogen bonding. And now between the two ammonia molecule, I want to do between two ammonia molecule. Let's see. Just draw the ammonia, one ammonia. Ammonia is trigonal pyramidal, nitrogen and three hydrogen. Hydrogen, hydrogen, and hydrogen. Nitrogen is highly electronegative, so negative charge, partial negative, partial positive, partial positive, partial positive. One more ammonia molecule, hydrogen, 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 partial negative, okay, partial positive, positive, slight positive. It's not ionic, so there is no ion swarm. It's just a polar molecule. Now, between hydrogen of one compound or one molecule and the nitrogen of another molecule, so this way. And how can we represent? By a dotted line. Can you try ammonia and water? Okay, let's the last one between the water and ammonia molecule. Okay, now the last one between water and ammonia. Let's see the water and ammonia. They will ask which of the compound has hydrogen bonding. Mostly they are giving HCl. I know most of the students that think HCl has hydrogen bonding. No, it's only between hydrogen and HCl and water there is hydrogen bonding, but not HCl and HCl. Now water and ammonia. Let's draw the water molecule. This is the water molecule, and slight negative, positive, positive, and ammonia, nitrogen, hydrogen, hydrogen, negative, positive, positive, positive. What's the shape of the water molecule? Bent. Yep, we have already discussed all the shapes. Now it's an interaction between hydrogen of water or hydrogen of ammonia, doesn't matter. Hydrogen to nitrogen or hydrogen to oxygen. Okay. Sometime they will give you a different molecule and they will ask you predict the hydrogen bonding and the following molecules. Okay, look at that. Draw the hydrogen bonding between two ethanol molecules. Can ethanol dissolve in water? Yes. First of all, ethanol is polar, water is polar, one reason. And the second strong reason is both they have hydrogen bonds. Let's draw the structure of two ethanol molecule, and we have to show the hydrogen bonding between ethanol molecules. Which functional group? It has alcohol, not ethanol. Nal is aldehyde. So two ethanol molecule, CH3, CH2, O hydrogen, partial negative, partial positive. All the time, guys, when you're drawing, when you come across the question asking draw the water molecule, draw the hydrogen bonding, you have to show the polarity or the dipole. And one more ethanol molecule, CH3, CH2, oxygen and hydrogen, partial negative, partial positive. So this oxygen, this hydrogen, you can pick anyone. So hydrogen of this one and oxygen of that one, or hydrogen of this one and oxygen of that one. Where did I put my... Oh, okay, look at that one. Oxygen of this one and hydrogen of that one. Draw the hydrogen bonding between the two ethanol molecules, this one. Now, predict which of the following molecule have hydrogen bonding. So H2S, like, so A is my H2S. I'm doing this question, guys. Hydrogen sulfide gas. B methane, CH4, C methanol, CH3OH, methanol, PH3, like ammonia. D phosphine, PH3 is phosphine, like ammonia, NH3 is phosphine. NO2, ENO2, meaning it's between two molecules, guys. Don't just take only one molecule. We have to compare between two molecules. Hydrogen bond is possible between two molecules. Intramolecular hydrogen bond is there, but I don't want to go in detail. When you would come across this question, meaning between two H2S molecule, hydrogen sulfide and hydrogen sulfide, between two methane, between two methanol, between two PH3 molecule, between two NO2 molecule, and one more, last one, methyl A B C D E F. F is methyl amine or aminomethane. Yeah. Now we will do one by one. Let's do. Can you guess it? Can you guess that, guys? H2S, hydrogen is there, but sulfur. Hydrogen and sulfur will not make hydrogen bond. So no. A is no. A, no hydrogen bond for H2S. No doubt hydrogen is there, but there will be no bond between hydrogen and sulfur. B, methane, hydrogen is there, but there is no highly electronegative element attached to methane. So no hydrogen bond. NO, no hydrogen bond. Methanol, we have done the ethanol. Yes, methanol. I'm not drawing, guys. They're not asking to draw it. Just we have to predict which one has the hydrogen bonding. Methanol, yes. I'm talking about two methanol molecule. See, methanol and methanol, yes, because of hydrogen and oxygen. Yes, we have. What about the PH3? Hydrogen is there, but phosphorus is not highly electronegative compared to nitrogen. So no for phosphine PH3, no hydrogen bond for PH3 molecule. If we compare phosphine and ammonia, yes, possible, but between two phosphine molecule, no. No between PH3 no. What about NO2? No NO2, there is no hydrogen. No. What about the two molecule of methylamine? Yes, methylamine. We have hydrogen and nitrogen. Yes, possible. Yes. So please, whenever you have a time, watch my video and do some revision. I want to stop here. Thanks for watching. Bye. Hi guys, welcome back to my channel. Let's start today's topic. I've already taught you hydrogen bonding and the definition of the bonding, and we have done past paper question based on the hydrogen bonding. Yeah, let's do the consequences of the hydrogen bonding. If the molecule has hydrogen bonding, that hydrogen bonding change the chemical and physical properties of that compound? Let's see. So chemical properties would not affect by the presence of hydrogen bonding, but physical properties are affected by the hydrogen bonding. Let's see. So look at the ammonia, NH3, and we have PH3, and we have ASH3, arsine, phosphine, stibine as BH3, and BiH3. All these are called hydrides of group 5 elements. Because of the presence of the hydrogen bonding in ammonia, it is highly soluble in water. Highly soluble. Highly soluble. Highly soluble in highly soluble in H2. And ammonia is polar. One of the reasons, but we are not looking the polarity of the molecule, but presence of hydrogen bonding make the ammonia molecule more soluble. Now these are called the hydrides of group 5 element, and we have hydrides of group 6 element, H2O, H2S, hydrogen sulfide, H2SE, hydrogen sulfides, telluride, hydrogen perluride. Same thing. Water has high boiling point, roughly 100 degree, and when you compare this, the boiling point is increases, but the boiling point is very low in case of H2S, then it increases. The reason behind this, it's large size. But why the water has high boiling point, more than 100 degree? Because of the presence of hydrogen bonding. Let's draw the graph. It goes like this, guys. Very high. Water has high. Water has high. Very high. Yeah. H2O high. Then we have H2S. We have H2SE. H2TE. Like that. Why the water has high boiling point? Due to the presence of H bonding, hydrogen bonding. And lastly, we have to discuss the hydrides of group 7 elements. Look at the group 7 elements like HF, HCl. Same, they are highly soluble in water because of the hydrogen bonding. They have high boiling point because of hydrogen bonding. HF, HCl, HBr, HI. Same thing. HF has high boiling point due to the presence of hydrogen bonding. HCl has the boiling point increases from here. Very high, decrease and increase. The reason why the boiling point increases from HCl to HI is due to the large size. Even though HF is a small size, but it has high boiling point. The reason behind is because of the presence of hydrogen bonding. You will get these kind of question in your examination, guys. Now, one more thing. When we compare ammonia, HF, and water, which of them has the highest boiling point? Let's see. Let's check all the three. The strongest hydrogen bond undoubtedly is present in HF because of high electronegativity of the fluorine. Look at that. I'm giving you one question. Among HF, comma, H2O and ammonia and H3, which one has highest boiling point? What's your guess, guys? HF? Okay. No doubt, the strongest hydrogen bond is present in HF. But the boiling point, when you compare to the boiling point, you can't say due to the presence of hydrogen bonding, all of them they have hydrogen bonding. So which one has the highest boiling point? Most of the student HF because of the strong boiling point. The answer is water molecule. Why the water molecule, sir? Water molecule has 2 hydrogen bond compared to HF and ammonia. Ammonia has one hydrogen bond, and HF also has one hydrogen bond. But when you compare water molecule, it has two hydrogen bonding. And because of the presence of hydrogen bond in water, it helps to make ice less denser, so that ice floats on water. Mostly, guys, when you look at the solid state of any compound, it should be more denser. But here, ice is the solid form of water, which is less denser than water. That's why it floats on the surface of the water. And look at the reason behind why ice is less dense than the water. Let's see. Ice is less denser than water. That's why it floats on the surface of the water. Ice has hydrogen bonding. Look at the structure of the ice. It forms like a open structure, open lattice. It's called open lattice. Look at that. So we have H2O. This is H2O. We have oxygen here, hydrogen and a hydrogen, hydrogen and hydrogen, hydrogen here also, partial positive, and one more hydrogen, one more hydrogen, one more hydrogen, one more hydrogen. So water has total 4 bond, 2 covalent bond and 2 hydrogen bond. Look at that. So it has 2 hydrogen, 2 hydrogen, each has 2 hydrogen. Look at that. 2 hydrogen, 2 hydrogen, partial positive, partial negative. Look at that. So we have slight negative charge. Oxygen is highly electronegative. Slight negative, 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 negative. Now look at the bond. Positive, 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 partial positive, partial positive, partial positive, partial positive, partial positive, partial positive, 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 partial positive, partial positive. Now, the hydrogen bond is present between highly electronegative atom like oxygen and hydrogen. So I told you 2 hydrogen bonds, 1 and 1, because it has 2 hydrogen, 1, 1, 1, 1, and it form a open lattice structure. This is called lattice structure of ice, or open structure of water. It form a cage-like structure. Again 2, again 2, again 2. So why there is a question, why the ice is less denser than water? The hydrogen bond present in the ice molecule make the water molecule apart. Why ice is less denser than water molecule? The presence of hydrogen bonds. How many? 2 hydrogen bonds in ice make water molecule apart. That's why it's less denser. We have kind of some space in that, which make the ice less denser than water molecule. Hydrogen bond is present in biological molecule also. Just I want to discuss briefly about biomolecule, only the DNA, because DNA has hydrogen bonding. Hydrogen bonding in biomolecules, like DNA is a biomolecule. DNA, deoxyribose nucleic acid. We know that DNA has a double helical structure. Guys, I'm not teaching biology, but I'm showing you the presence of hydrogen bond in DNA. It has a double helical structure. The DNA has a double helical structure like this, and a DNA has some nitrogen bases, which is like, for example, A, T, C, G, adenosine, thymine, cytosine, glycine. So they are connected. So these two strands, single strand, are complementary to each other, and they make a bond with the help of hydrogen bonding. They make a perfect shape due to the presence of hydrogen bonding. So between A and T there is 2 hydrogen bond, and between C and G there is 3 hydrogen bond, which make the molecule perfectly helical structure. So it's called alpha helical. So the bonding, the pair between A and T, it's because of the 2 hydrogen bond, and the pair between C and G is because of 3 hydrogen bonding. One more thing, the secondary structure of our protein molecule is also contain hydrogen bond, and some cellulose molecule, not some, my bad, cellulose molecule, which is a linear molecule. Look at the cellulose as a polysaccharide. It is a polymer of beta glucose, and it form a linear structure which is alpha coil, or which is a coil structure. That coiling is called alpha coiling because of right-handed coiling. Each linear structure bind to another linear structure with the help of a bond, which is nothing but a hydrogen bond, and that makes the molecule more strong. This is also called cross bridges. So in biomolecule DNA, the structure of the perfect structure of the DNA is because of the presence of hydrogen bonding. Secondary structure of the protein is due to the presence of the hydrogen bonding, and they also form some cross bridges. It has alpha helical and a beta pleated structure. Proteins, secondary structure of the protein. Secondary structure that has hydrogen bonding. Cellulose, which is a carbohydrate. Cellulose is a polysaccharide, which is a polymer of beta glucose, and it is a linear molecule, not the branch like a starch and glycogen. And each linear structure is coiled further, and these two coil, they join together by means of the hydrogen bonding. So this is hydrogen bond, H bond. Here protein has hydrogen bond, and these are also hydrogen bonds. Okay, so many importance of hydrogen bonding. First of all, due to the presence of the hydrogen bonding, it is highly soluble, and it has more boiling point. Hydrogen bond is a weak electrostatic force of attraction between the two molecules. Okay guys, now I want to stop my video here, and in my next video, hopefully I'm going to teach a permanent dipole interaction, and lastly induced dipole and induced dipole. Thanks for watching my video. Welcome back to my channel. Hope you are doing well. Let's start today's topic here. Permanent dipole. In my last video, I've already explained about hydrogen bonding. Now, look at the permanent dipole, which is also called PDPD. Now, you know that I explained in my covalent bonding topic, we have a polar covalent compound. How can we choose whether the compound is polar or non-polar? Based on the difference in electronegativity. Suppose I have A and a B, two elements of a different element, and if there will be a difference in electronegativity, then the molecule is said to be polar. like I have A and A, there will be no difference in electronegativity, like chlorine molecule, oxygen molecule, and hydrogen molecule, nitrogen molecule, fluorine molecule, chlorine, fluorine, nitrogen, oxygen, yes, bromine, I2. The electronegativity difference is zero. Delta E electronegativity difference is equals to zero. So such compounds are called nonpolar. But some compounds like, for example, HCl, A and B type, where electronegativity of hydrogen and chlorine are not same. There will be a difference in electronegativity. Like for example, I have HF, hydrides of 7th group element, HCl, HF, HBr, HI. So the difference in electronegativity, delta En, is not equals to 0, 100%. So such molecules are polar molecules, and they have permanent dipole, permanent dipole. And I'm keep on telling you guys, this dipole-dipole interaction is a type of force between two molecules. So it is not a force, means it is not a type of bond like a covalent bond, ionic bond. It is not a bond, it is a type of interaction between two different molecules. If suppose I have HF or HCl, take the example of hydrogen chloride, HCl partial positive, partial negative, and one more HCl molecule, H and Cl minus. So that chlorine and hydrogen will interact each other. So this type of bond is called permanent dipole-dipole interaction. So in all the polar molecule where the difference in electronegativity is not equals to 0, such molecules have PD, permanent dipole, permanent dipole. So most of the students ask me a question, sir, all the polar molecules, they have PD. Some polar molecule, they're polar, but they don't have a PD. How can we check whether they have a PD or induced dipole? First of all, did you get it? All the molecules of AB type, what does it mean, sir? These are two diatomic molecules like AB type, and there should be a difference in electronegativity, like delta En is not equals to 0, then such molecules have PD interaction. Now check the polar molecule which has PD or ID. Let's check the polar molecule. Rather, I have to say polar compounds which has more than 3 elements or more than 2 elements. For example, look at that. We have BF3 and ammonia. Ammonia is a polar, and a BF3 is non-polar. So check all the polar molecules whether they have PD or ID. Let's check. We have two molecules like very close, like ammonia and BF3, or NF3 and BF3. Let's check. BF3, look at the NF3 and nitrogen trifluoride, and BF3, boron trifluoride. So look at the NF3 and BF3. NF3 is polar, BF3 is non-polar. What is the criteria to check whether they are polar or non-polar? Here we have a dipole. We have to check the dipole. Rather than the net dipole. Net dipole of compound. I've already explained, guys, about the net dipole, resulting dipole in my previous videos. Look at that. There is a net dipole, 100%. Check net dipole. So if there will be no net dipole, check dipole, no net dipole. Dipole cancel off. If there is a net dipole, the molecule is said to be polar. If there will be no net dipole, the molecule is said to be non-polar. So all the polar molecules have PD-PD interaction. So make a note, all polar molecules or compounds have what type of interaction? PD-PD, permanent dipole. I'm coming to non-polar. Molecule, guys. So PD-PD. So first of all, we have to check difference in electronegativity. If the difference in electronegativity is not equals to 0, then the molecule is said to be polar. If the molecule is polar, then it has PD-PD interaction. Permanent dipole. Like, for example, I have one more example. Like we have CO2 and which one is CO2 and carbon, which have, so, and we have, let's check water molecule, 2 lone pair is 100% polar and a PD-PD. How can I check? I will give you one more hint, guys. All the polar molecules have PD-PD interaction, and check the symmetry of the molecule. If the molecule has perfect symmetry, then it has no PD-PD interaction because there is no net dipole. And if the molecule has a lone pair, then it is a polar molecule and it has PD-PD. So you are confusing me. I will come back to this explanation. Okay. Now, so first of all, AB type and AA type. AB means difference in electronegativity. Difference in electronegativity is not equals to 0. Difference in electronegativity, delta E, difference in electronegativity is equals to 0. What type of force of attraction? What type of intermolecular force of attraction? PD-PD, guys. PD-PD. If there will be no PD-PD, what's the another type of intermolecular force of attraction, which is called induced dipole? I will explain you what is meant by the term induced dipole, ID. Another name of induced dipole, another name, van der Waals force of attraction, London forces, van der Waals force of attraction. Van der Waals force of attraction, WAALS. Waals, van der Waals force of attraction. Yeah, ID. Now, if a molecule is polar molecule, polar, non-polar, all the polar molecules which are non-symmetrical, polar, non-symmetrical, mostly polar molecules are non-symmetrical, like ammonia, you can't cut the molecule into 2 equal half because there will be a net dipole, polar, non-symmetrical, and presence of lone pair. What are the conditions? They should, if a molecule has a lone pair, then the molecule is polar, non-symmetrical, and presence of lone pair. So instead of confusing which molecule is polar, which molecules has PD, which molecules are ID. I'm giving you generalized terms. Check the polar molecule. If it is a polar, then hopefully polar molecule followed by non-symmetrical shape, or asymmetrical shape, polar, non-symmetrical shape, presence of lone pair. All they have PD. Non-polar molecule, non-polar, symmetrical. I will give you example, guys. Non-polar, symmetrical, non-polar molecule, symmetrical, no lone pair, non-polar, symmetrical, because net dipole cancel off, no lone pair absence, no lone pair, absence of lone pair. You can cut the molecule into equal half, symmetrical, no lone pair, then it has ID. All the molecules which are perfectly symmetrical, like we can start from tetrahedral molecule. Yeah, all the group 4 element having 4 monovalent atom, like tetrahedral molecule. Check the tetrahedral molecule. Okay, now check the tetrahedral molecule, guys. Can I rub that one? Okay, now look at the tetrahedral molecule. So what are my two conditions? My two conditions, I will write one more time. My two conditions: polar molecule, presence of asymmetrical, no symmetry, presence of lone pair. They have PD. You can say, without looking the molecule, means without drawing the shape and all this thing, check it's polar molecule or not. Yes, it is a polar molecule. Check it has symmetry or not. If there will be no symmetry, polar molecules are non-symmetrical. Polar molecule non-symmetrical, and presence of lone pair, so they have PD. Simple. Let's start. So what are the condition? Let's start. NH3, trigonal pyramidal. No, let's start. Okay, this is polar. Okay, no worries. Trigonal pyramidal. I'm talking about the polar molecule with the lone pair. Polar molecule, polar. Okay, that's my condition. Next condition: asymmetrical, non-symmetric or non-symmetrical, asymmetrical, presence of lone pair present, lone pair of electron. So what type of intermolecular force of attraction? PD, guys. PD. All the fifth group element having 3 monovalent atoms, like NCl3, NF3, NBr3, Ni3, as long as central atom has a lone pair of electron. So non-symmetrical, polar non-symmetrical, PD. Now come to group 6 element, guys. Come to group 6 element. They have lone pair also. So group 6 elements: H2O, H2S, H2O, H2S, H2SE, H2TE. Look at that. 2 lone pair. So if such molecules will come in the past paper or will come in the examination, I've seen this question in many past paper. If they will come in the examination, you can say, you can do all these, like You can check whether they have whether they have whether they are polar or symmetrical molecule or PD. First of all, are they polar? Yes. What is the condition? Non-symmetrical. I can't cut the molecule into two equal half, guys, because of the presence of lone pair. So undoubtedly, non-symmetrical, polar, 100% polar. They are polar. They are polar. Polar. All are polar. They are polar. Polar. Okay. They are polar. Non-symmetrical. Second condition. First condition. Yes, polar. Non-symmetrical. Yes, non-symmetrical. I cannot cut the molecule into two equal half. Presence of lone pair. Yes. So what type of intermolecular force of attraction they have? Blindly. PD, guys. PD. They have PD. They have PD. Now we have already done HCl, HF. So we have done HF. Difference in electronegativity is not equals to 0. So they are polar. Polar meaning unsymmetrical. We can't cut into two equal half. So unsymmetrical meaning PD. What type of intermolecular force of attraction? PD. And blindly rest of the molecule which are symmetrical, absence of the lone pair, they have ID. Induced dipole. The dipole is not existing in the molecule, guys, but because of the oscillation, I will teach you, a dipole is created in that molecule. So that's why it is called induced. It caused by ID. Look at that. So any molecule which are polar molecule, non-symmetrical, presence of lone pair, what type of intermolecular force of attraction? PD. Sir, you are repeating. Yeah, that's good for you. Okay, PD. Now, all the symmetrical molecule. Okay, let's check the symmetrical molecule. All the symmetrical molecule, tetrahedral molecule, perfectly symmetrical. Tetrahedral molecule. Non-polar, sir? Yes, non-polar. Tetrahedral, like methane molecule. All the tetrahedral molecule. CCl4, tetrahedral molecule. Tetrahedral molecule. Tetrahedral molecules. Tetrahedral molecule examples. I have given so many examples. Please, you can see my previous videos for tetrahedral molecule. Like methane is a tetrahedral molecule, sir? Yes. CCl4 is a tetrahedral molecule? Yes. Carbon is a central atom. So central atom is from group 4, having 4 bonded pair of electron and a no lone pair. So what's the condition for induced dipole? Non-polar. First condition, non-polar. Yes, non-polar. Is there PD? Non-polar. Okay, non-polar. One condition is non-polar. Symmetrical. 100% tetrahedral, symmetrical. There will be no net dipole. Symmetrical, no net dipole. Absence of lone pair, obviously, no lone pair. So what type of intermolecular force of attraction? ID. Now, after that, we can't go to the trigonal pyramidal molecules. They have lone pair of electron, so non-symmetrical. They have PD. Now, after trigonal pyramidal, we have we have nonlinear molecule. Check the nonlinear molecule. I want to check the nonlinear molecule. All the nonlinear molecules. like H2 or H2S, which has a, which has lone pair. So uh, it has PD. So after that we have trigonal trigo trigonal planar molecule like a BF3, boron trifluoride, perfectly symmetrical, 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 symmetrical. Non-polar condition, non-polar, symmetrical, no net dipole, yes. So ID, all trigonal planar molecule have ID, induced dipole. The dipole caused by, it has no permanent dipole. After that, trigonal bipyramidal molecule, trigonal bipyramidal, okay, trigonal bipyramidal, okay, trigonal bipyramidal, PCl5, no lone pair, guys. Example, PCl5, symmetrical, yes, symmetrical, non-polar, first condition, non-polar, second condition, symmetrical, presence of lone pair, no lone pair, no lone pair of electron. So what type of intermolecular force of attraction? ID. We have octahedral molecule. Let's do the octahedral molecule now, like tetrahedral molecule, octahedral molecule. Example of octahedral molecule, SF6, tetrahedral, octahedral molecule, octahedral SF6 molecule. I'm going to draw here, guys. SF6 molecule, perfectly symmetrical. There will be no net dipole. So what are the information? Why this molecule has no PD? Like, first of all, non-polar, SF6, non-polar, yes, non-polar, symmetrical, yes, symmetrical, no net dipole, all the dipole cancel off, no net dipole, non-polar, no lone pair, absence of lone pair, no LP, lone pair of the electron. So ID, induced dipole. So can I give you one more example? A square planar, like a octahedral square planar, easy one. Square planar, all these square planar molecule. So look at that. Any molecule which are polar, having a polar molecule without a lone pair, no net dipole, are having PD interaction, permanent dipole. So one more condition. The another condition is like that: non-polar, symmetrical, no lone pair, no net dipole, then the molecule has induced dipole interaction. Guys, I want to stop my video here. Thanks for watching. I will come back with a new video. Bye. Guys, welcome back to my channel. Hope you are all doing well. Today we are learning van der Waals forces of attraction among the molecule. In my previous video, I already taught about the induced dipole. So which molecules or the compounds have induced dipole? I didn't teach you how the van der Waals force of attraction arises in the molecule. Let's see. Van der Waals force of attraction is caused by the movement of the electron. The movement of the electron, VW, van der Waals force of attraction, van der Waals forces of attraction are caused by the movement of electrons in the molecule, in the compound, or in the molecules. Okay, now what happens when the electron move? That causes charge dispersion, and which indirectly causes a partial dipole. Look at that. So this is the molecule. This movement of the electron causes a charge dispersion. So this end become a positive end, and that end become a negative end. That causes the partial dipole in the molecule. Okay, suppose one more molecule is there. This is non-polar molecule, guys. Suppose we have one more molecule. Look at the one more molecule. That one more molecule. I have one more molecule. Look at the one more molecule. Okay. Which is a non-polar molecule. If that molecule comes close to that molecule, it's just like this molecule is just like a balloon. That movement of the electron cause instantaneous dipole in that molecule. That instantaneous dipole, so it creates an instantaneous dipole in that molecule. So it has a very weak partial positive and a partial negative here. Suppose this molecule is coming close together, and because of this charge distribution, this molecule oscillates. It rotates. That oscillation of the molecule causes or induce a dipole in another molecule. That induce a dipole here, induce a weak dipole. This become a negative positive, and that become a negative. So it's very weak, partial and a partial. So one more time, guys, look at that. Van der Waals force of attraction are caused by the movement of the electron. When the electron move in the molecule, positive charge fixed at one side, that causes an instantaneous dipole or a very weak dipole. When the two molecules come close together, that molecule oscillate. So positive end attract with the negative end, so like this. So this instantaneous dipole induce a dipole in another molecule. That's why it is called induced dipole and induced dipole. Look at that. Whether the molecule is polar or non-polar, they have induced dipole. Every molecule has induced dipole attraction. Mainly the non-polar molecule have induced dipole. Let's see the consequences of the van der Waals force of attraction. Okay, so just a moment. What happens if the molecule has a 1 volt force of attraction? So it is caused 1 volt force of attraction are caused by the movement of the electron. As the number of electron increases, 1 volt force of attraction also increases in the molecule. Now look at the consequences of 1 volt force of the attraction. 1 volt force of attraction is directly proportional to the number of the electrons in the molecule. That electron cause a weak dipole in the molecule. Look at the weak dipole in the molecule. This is the molecule and it causes a weak dipole. So this and partial positive, partial negative. So due to the presence of 1 volt force of the attraction, the boiling point of the molecule increases. Now look at that question. Look at the halogens: fluorine, chlorine, bromine, and I2. So it's a past paper question. Why I2 exists in the solid form? That's the gas, liquid at room temperature and solid at room temperature. What's the answer? No doubt, all of them they have induced dipole. But as the number of electron increases, as the look at the size of the iodine, it's a bigger size. As the number of electron increases, the induced dipole also increases. That's why iodine exists in the solid form at the room temperature. So the answer is more 1 volt force of attraction for I2. Yeah, you know that. So what are the consequences of 1 volt force of attraction? Boiling point increases due to the presence of 1 volt force of attraction. The molecule has more boiling point. So let's check one more example of 1 volt force of attraction. Like 1 volt force of attraction is also called as induced dipole interaction, and it is also named as London forces. Now look at that. What happened? I will give you one more example of 1 volt force of attraction, which is also called induced dipole. Induced dipole. Why we are calling induced dipole? No doubt it is an instantaneous force of attraction between the molecule, but that cause induced dipole to the another molecule when the molecule oscillate. Okay, look at that. Alkene. We have alkene. Look at that. Alkenes are non-polar. We know that alkenes are non-polar. Non-polar meaning ID, induced dipole. Look at that. Alkenes, they are non-polar. When the bromine approaches, bromine is also non-polar. Bromine molecule is non-polar. When the bromine approaches, this double bond, which is a pair of the electron, causes a dipole in the molecule. This causes a partial positive and a partial negative. That causes a dipole in the molecule. So this is also an example, best example of ID. I told you that all the non-polar molecules, they have ID or weak intermolecular force of attraction. Let's check the strength of the intermolecular force of attraction. I have already discussed two of them, hydrogen bonding and permanent dipole. That's the third one. The last one is ID. Look at the strength of all these intermolecular force of attraction. First, hydrogen bonding. Hydrogen bonding is the strongest one because it's the type of electrostatic force of attraction. Hydrogen bonding, first one, hydrogen bonding, H bonding, and second one is permanent dipole PD, and the third one is ID, which is also called van der Waals force of attraction. Now, this is the property of polar compound, and this is also the properties of polar compound. It is present when the molecules have hydrogen atom along with highly electronegative atom such as fluorine, nitrogen, and oxygen. Okay, this type of intermolecular force of reaction present in the polar compounds, and this is present in the non-polar compound. How can we check the compound is polar and non-polar? So polar and non-polar. So polar compound has PD, and non-polar compound has van der Waals force of attraction of ID. Non-polar. Polar, there is a difference in electronegativity. Electronegative value is not equals to 0. Electronegative value, difference in electronegativity is equals to 0, is not equals to 0. One more thing, the molecule is unsymmetrical, yeah, the molecule is symmetrical. All the well-known shape of the molecules, like we have tetrahedral shape. So here examples, TD shape tetrahedral. Then we have trigonal planar, trigonal planar, and we have trigonal bipyramidal, we have octahedral, OT complexes, square planar complexes, and those molecules which are polar, unsymmetrical, they should contain a lone pair of electron, like ammonia, polar 100%, water polar, and we have some such compounds which has a lone pair, symmetrical. And the dipole here, the dipole moment cannot cancel off. There will be a resultant dipole. Here, dipole moment cancel off. Look at that. We have ionic bonding, like ionic covalent. I want to compare ionic covalent, permanent dipole interaction, and van der Waals force of attraction, which is induced dipole. Ionic, 1,000 times greater. Ionic bonding, strong bonding, which is a very strong bonding, guys. Then we have a covalent, then we have which is greater than covalent. Then we have PD, sorry, then we have hydrogen bonding, which is greater than dipole interaction. Dipole meaning PD, permanent dipole. The lastly we have van der Waals force of attraction. Van der Waals force of attraction. That's the strength. We know that. Like a very quick review: ionic between metal and non-metal, covalent between two non-metals, hydrogen is not an actual bond. Hydrogen bonding is not an actual bond. It is a type of intermolecular force of attraction between two molecules. One of the molecules should contain hydrogen atom, and the other molecule should contain either nitrogen or oxygen or fluorine. Dipole interaction The van der Waals force of attraction is also a dipole interaction, but mainly dipole interaction meaning PD-PD, which is present in the polar molecule, and van der Waals force of attraction is present in non-polar molecule. So any molecule, the weakest bond, if they will ask you what type of force of attraction is present in non-polar molecule, you can blindly say van der Waals force of attraction, which is the weakest force. So for example, H2O, and I will give you HF. Look at the HF molecule, HF and H2O, and we have HCl, I2. Predict the type of intermolecular force of attraction. We are not talking about ionic bonding and covalent bonding. So look at the question. Predict the type of intermolecular force of attraction among all these molecules. So this is A, this is B, C, D. Hydrogen bonding, H bonding, hydrogen bonding plus, because it's polar molecule, plus PD-PD. And I told you every molecule should have van der Waals force of attraction. So it has van der Waals force. Van der Waals. Yeah. Now come to the hydrogen. Come to the water molecule. Same thing. Hydrogen bonding. It has hydrogen bonding. H bonding, which is a stronger force of attraction when you compare to PD-PD and van der Waals force of attraction. So it has one. What's the one? Hydrogen bonding. Yes, it has hydrogen bonding plus PD-PD plus van der Waals force. Okay. Now HCl. HCl has, can you guess? HCl has only PD-PD and van der Waals, no hydrogen bonding. So HCl molecule has PD-PD plus van der Waals force of attraction. And the last one, I told you the last one, no hydrogen bonding, obviously, no PD-PD, non-polar molecule. It has only van der Waals force of attraction. Van der Waals force of attraction. So they will ask you such question, like they will give you ammonia and they will ask you predict the type of intermolecular force of attraction. So ammonia, let's do ammonia one, guys. Let's do one example, ammonia. Ammonia, when you come across like a compound having hydrogen and a nitrogen, definitely hydrogen bonding, like ammonia. They will ask you why the ammonia is highly soluble in water compared to the other hydrides of fifth group element. We will do the example. Why ammonia is highly soluble? Why NH3 is highly soluble in H2O. One thing, hydrogen bonding. So strong electrostatic force of attraction or intermolecular force of attraction. B, ammonia is polar, NH3 is polar. So it has PDP, permanent dipole, and lastly, each molecule has van der Waals force of attraction. C, lastly, ID, which is also called van der Waals force. Van der Waals force of attraction. Ammonia is soluble in water. Then come to pH3, ASH3, SbH3. Yeah, polar. And then which one is highly soluble? As the size increases, solubility increases. So guys, I want to stop my video here. I will come back with a different topic in my next video. Thanks for watching. Hi guys, welcome back to my channel after a long time. Hope you are doing well. I have a fever, cold, that's why I did not make my video. So let's see, let's start the metallic bonding today. Look at that. It is present within the metal. We think that it is present between two metals. That's the wrong thinking, wrong idea. Most of the students are thinking the metallic bonding is present within or between two metals. It's not between two metals. Metallic bonding is present within the metal, within the crystal of the metal. It's called lattice. Look at this. So it is a electrostatic. It is an electrostatic force of attraction between fixed positively charged ion, fixed positive charged ions and delocalized electron. So the electrons are delocalized, and it is an electrostatic force of attraction. Whenever we have the formation of the ions, then we are using the term electrostatic. It creates electricity. So we know that all the metals in any form, like solid state, liquid state, gas state, I'm giving an impression that liquid metals are there, gaseous metals are not present, but they can conduct electricity. Like ionic compound in solid state can't conduct electricity, but the metals can conduct electricity all the time because they have free delocalized electron. So we can also say that a giant lattice, a giant metallic lattice, a giant metallic lattice is also referred to as lattice of fixed positive ions surrounded by delocalized or surrounded by sea of electron. So it's just like a sea of electron, surrounded by sea of electrons. So the attraction between the positive ions and by the movable electron, it's called the metallic bond. So it's a strong bond, very strong bond. So each positive charge here is surrounded by more than 2 electrons because the electrons are moving. So please copy down that one. So it is like I will draw the structure, guys. A giant metallic lattice, because it forms a perfect shape, that's why it's called lattice, is also referred to as a lattice of fixed positive ions. Positive ions are fixed, surrounded by sea of electrons. Okay, can I rub the boat? Now look at that. Now look at that. Draw the metallic bonding in sodium or magnesium. So we know that this is present within the sodium metal, and is the sea of the electron. Positive charges are fixed. So fixed positive charges, lattice of positive fixed charges, and the sea of electron. delocalized electron. Electrons are moving, and each positive charge is having more than two or more negative charge, which is delocalized electron. So positive charge, fixed positive charge, lattice of fixed positive charge. Positive charges are fixed and the electrons are delocalized. Electrons are moving, they are not fixed. That's why each positive charge has more than two electrons, which make metallic bond strong force of attraction. Whenever we use the term electrostatic, means it creates electricity, it produces electricity. This is the structure of Na metal. I will draw for magnesium. Please copy down that one. So positive charges are fixed and electrons are delocalized. That's why it creates electricity. So each positive ion has more than two electrons. Okay, now come to magnesium. Metallic bond in magnesium. Please keep on telling that it's not between two metals. Metallic bonding is within the metal. It's present within the metal. Metallic bonding within the metal. Very strong bond. We need a lot of energy to break that metallic force of attraction between the positive ions and the electrons. That's why it has highest melting and boiling point. I'm coming to the properties. I want to draw the metallic bonding in magnesium. They will ask you magnesium, sodium and aluminium, at the most aluminium. Look at the magnesium one. So fixed lattice structure, it's a lattice structure having fixed positive charge. Magnesium has 2 plus, guys, you have to draw 2 positive charge. That's the trick, 2 positive, or that's also possible, 2 plus. Either put 2 plus charge or 2 positive charge, both are fine. 2 positive charge, I want to put 2 plus inside, I want to put 2 plus inside. 2 positive. Sodium lost 1 electron, magnesium lost 2, magnesium lose 2 electron, so 2 plus, 2 plus, 2 plus, 2 plus, 2 plus, 2 plus. For aluminium is 3 plus, 2 plus. Magnesium is in the group 2, that's why it's 2 plus, 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 and the sea of electron. Look at the sea of electron. We have a lot of electrons moving here and there. That's why we use the term delocalized electron. The electrons are not fixed, they are moving, that help to conduct electricity. Okay, now quickly I want to go the properties of metallic bond. First, we know that between the negative charge and the positive charge there is a strong electrostatic force of attraction. That's why we need a lot of energy to break it. So they have high melting point and a boiling point. First, they have high melting point and a boiling point. They have high melting and boiling point. They are the good conductors of heat and electricity. When you heat the metal, all the electrons vibrate and heat transfer. Those electrons, they vibrate first and transfer the heat energy from one place to another place. Hold the spoon. Suppose this is the candle and you can hold your spoon here. After some time you can feel the hotness here. That's the spoon. So it means heat transfer from one part of the spoon to the another part, because the positive ions are fixed and the electrons are moving, so heat energy transfer. So they are the good conductors of heat and electricity. They are the good conductors of heat and electricity. All the metals, almost all the metal can conduct electricity in the solid form, in the liquid form. Ionic compounds cannot conduct electricity in the solid state because there will be no movement of ions. But here, electrons are moving here and there, which is responsible for the conduction of electricity. Now, two more important properties of the metal. We have lots of properties of metal. I don't want to discuss everything here. Now, two more properties: malleable and ductile. Malleability and ductile. They are malleable and ductile. Malleable and ductile. What is meant by the term malleable? We can mold them into wires, long wires, copper wires. Ductile, we can turn them into any shape. Metal can form any shape. So they are good for malleability and ductility. Malleable and ductile. These are the important properties of the metals, guys. What are they? Malleability, they are malleable and they are ductile. What is malleability? Mean we can make the metals into long wires. Long wires, change them into long wires, copper wires. All these, the internet, they are passing through the long wires, and ductility into different shapes, into different shapes. We can change the metal into any shapes. Malleable and ductility. So these are the important properties of the metal. They have high melting point, they have high boiling point, they are the good conductors of heat and electricity, malleable and ductility. Now, I want to teach here a giant ionic lattice, because metallic lattice, metal is like a metallic lattice. The repeated unit of a constant shape is called lattice. So after that, I want to teach ionic lattice, especially NaCl. I've seen many questions that comes into the past paper from NaCl structure or CSCl structure. NaCl, we will discuss first NaCl structure. Sodium chloride. Sodium chloride is not a simple molecule, it's a giant ionic lattice. Now, sodium chloride, NaCl, sodium chloride. Ionic compounds form lattice structure easily. Best example, NaCl. They in that case, so ionic lattice. Bonhoeffer is a scientist. He used to work out the lattice enthalpy. I will teach you, guys. When the ions come close together, it forms an ionic bond, and that ionic compounds have a perfect shape, symmetry. That symmetry is called a lattice structure, and these units are repeating. So ionic lattice, so they have oppositely charged ions. surrounded by different sites, by different sites. They have oppositely charged ions surrounded by different sites. So each ion is surrounded by many others oppositely charged ions. We will see the example of NaCl. That's why they have a strong force of attraction, very strong force of attraction. Look at the NaCl. I'm not the artist, guys. I will try to draw the cube. This is the cube. Cube has 6 faces, and at the center we have sodium. So you have sodium here and chlorine, 6 chlorine. So each Na plus in NaCl lattice, each Na plus is surrounded by 6 Cl minus and vice versa, because one more unit repeats here, one more unit repeats here. That's my sodium. We have a big structure for chlorine. Chlorine is the bigger atom. So we have chlorine here, we have one more chlorine at the corner, one more chlorine. So we have 6 chlorine, one more chlorine at that side. So one more chlorine, one more chlorine. So we have 6 chlorine because each cube has a 6 faces, and each Cl minus is surrounded by 6 Na plus, because we have one more unit here, one more unit here, one more unit. It's very large, it's very big unit. You can easily see this model in your lab or in your laboratory. So NaCl is a perfect giant ionic lattice. So each Na plus is surrounded by 6 Cl minus. They have oppositely charged ion surrounded by different sites. That's why it has a very strong force of attraction. One more question. Can a solid NaCl conduct electricity? No. Only when the NaCl is in the molten form or in the aqueous form, then only it can conduct electricity. My question is that why solid or lattice, not the solid, my bad, why the lattice NaCl do not conduct electricity? Simple reason, because the ions are not free to move. So it is called, actually, that is called the phase center cubic, but don't worry about it. So we have cesium chloride also. Cesium chloride, each cesium is surrounded by 8 Cl minus. Here each sodium is surrounded by 6 Cl minus. That was a past paper question. So guys, please do the revision on all the ionic bonding or the chemical bonding. You can watch my videos. I just want to teach one more topic in the series of the bonding, that is giant covalent molecule. I didn't teach you the giant covalent molecule. Then after that, I want to compare the properties of the ionic, metallic, giant ionic, giant covalent, simple covalent. Thanks for watching my videos. Hope you are doing well. Welcome back to my channel. Today I'm going to teach you giant covalent molecule. In my previous video, I have done metallic bonding, and this is the last topic of the bonding. Look at that. In the giant covalent molecule, we have a diamond, graphite. Some books I have seen as silicon dioxide. Let's start with the diamond and the graphite. diamond and graphite. Diamond, look at the diamond. So each carbon is bonded with 4 different carbon and they link with each other and the structure grow. So this carbon again 1, 2, 3, 4. So 1, 2, 3, 4 like this. Diamond is a hard molecule. In case of graphite, look at the graphite. Graphite, don't worry, I'm giving you notes. Each carbon, look at this carbon, is bonded with 3 other carbon and make a hexagonal layer. Each carbon is bonded with 3 other carbon. We have 3 other carbon. Look at here. Each carbon is bonded with 3 other carbon and make hexagonal layer. Look at that one. One hexagonal layer and one more hexagonal layer. You have one more hexagonal layer. Okay. Now look at the difference. Generally for 3 marker they will ask the difference between the diamond and the graphite. Look at that. So here each carbon is a tetrahedral in shape. Carbon is tetrahedral. Here each carbon bonded to 3 other carbon. Each carbon is bonded to 3 other carbon atoms. That make the molecule softer. Why? Look at that. No doubt it has a strong covalent bond. So this graphite has hexagonal layer. Carbon is tetrahedral, hard, soft. Why it's soft, I will tell you. Carbon has lot of a strong covalent bond. That's why it has high melting point, very high. It is like a rock, high melting point, very high melting point. High melting point comparatively less in case of graphite than the diamond. So when the diamond sublime become vapor form at 3800 Kelvin, guys. That much temperature needed to make the diamond into vaporized form. A lot of temperature needed. It has more covalent bond, strong covalent bond. But look at the gap. Look at the distance. The distance of the covalent bond is less than the gap between the layers. First of all, the layers slide one over the other. The layers are slippery. Hexagonal structure. What's the structure? Hexagonal. Layers are slippery. Layers slide one over the other, which make the molecule soft, and it is used as a dry lubricant. I want to rub this part. Yeah, this is soft, hexagonal. Layers slide over other. So graphite use as dry lubricant. Dry lubricant. And one more point of the hexagonal layer. Look at this gap. This gap, the atomic distance. This is a covalent bond. The bond length of covalent bond is less than the gap. This gap is more high, which make the molecule more lighter. That's why graphite is less dense. Density is very low. Density of the graphite molecule is less. Look at that. Graphite is less dense, or the density of the graphite molecule is less low. The graphite has less density, has low density. So it is used as lightweight equipment, sports equipment. The melting point is very high, but compared to diamond, it's low. High melting point, and why the layer slide one over the other, it has a weak one over force of attraction. So melting point is high melting point, no doubt. Melting point is very high, but the diamond has highest. When you compare simple covalent bond, it has high melting point because of more one over force of attraction. High melting point, high melting point. Okay, the layers slide one over the other because it has a weak one over force of attraction. The layers are slippery, slide over each other, having weak van der Waals forces. Okay, important point, diamond is the good conductor of heat, such as graphite. Diamond cannot conduct electricity, guys. In diamond, each carbon is bonded to 4 other carbon, so all its valence electron is used. Diamond is a bad conductor of electricity. Oh, diamond can't conduct electricity. Diamond is a good conductor of heat. It's a good conductor of heat, very good conductor of heat. Diamond is a good conduct of heat energy, but can't conduct electricity. Whereas graphite does. The reason behind is that in graphite, each carbon, look at the carbon, each carbon, suppose this is the carbon, I want to highlight that. Suppose this is the carbon, it make, or this is the carbon, suppose it make 1 bond, 2 bond and 3 bond. The 4th electron is free, and that 4th electron is moving between the layers. So we call that electron as a delocalized electron, and it's moving freely moving in the graphite structure in between the hexagonal layer. That's why graphite can conduct electricity due to the presence of delocalized electron. Graphite can conduct electricity due to the presence of delocalized electron. Okay, but diamond can't conduct electricity. In diamond, each carbon has 4 bonds. Each carbon use all its valence electron. So graphite, look at the graphite. Graphite can, very important point guys, 3-mark question for the GCSE and for the A level exam. Graphite can conduct electricity due to the presence of delocalized. You can underline delocalized term, delocalized, freely moving, delocalized electron. In case of ionic bond, you have to mention free ions. In case of metallic bond, delocalized electron. Why the metals conduct electricity? Because of presence of delocalized electron. Why the graphite conduct electricity? Because of the presence of delocalized electron, and that electron move between the layers. The layers has very less gap. Okay, graphite is used in pencil. Diamond is hard, so it is used to cut the tools, to cut glass, used in pencil. Okay guys, we have one more giant covalent structure along with that graphite and a diamond. Any guesses? Silicon dioxide. Okay, write down one question. Look at the solubility of graphite and diamond. Diamond is highly insoluble. It's not soluble. Both are not soluble. Do not soluble in any solvent. Same as graphite. Not soluble in any solvent. Not soluble in any solvent. Okay. Along with that, we have one more compound of giant covalent compound. Just copy down that question. The boiling point of CO2 is less than SiO2. What's the reason? SiO2 is a giant covalent compound. CO2 is a CO2 is a simple covalent compound. Carbon dioxide, simple covalent. It's micromolecule, it's not the macromolecule. This is the macromolecule. Simple covalent. And look at the structure of SiO2. SiO, so it has more 1-volt force of attraction. I'm not sure that the structure was once asked in the past paper. I'm not sure which board of exam. SiO2. Silicon dioxide. Why the boiling point of silicon dioxide is higher than the carbon dioxide? Because it has more 1-volt force of attraction. It's not a simple molecule, it's a giant molecule. More van der Waal force of attraction. Force of attraction. Okay. One more question. Why the P4, the boiling point of the boiling point of P4 is less than S8. You know the diamond graphite, they are called allotropes, guys. Like they have similar element but different structure. They are called allotropes. These two are called allotropes. Allotropes. Similar element but exist in different form. In that we have fullerenes, but I'm not going to teach fullerenes. The fullerenes, C60, C80, diamond graphite, they all are called allotropes. Now P4 and S8. Let's check the boiling point of P4 and S8. So why you have written P4? Phosphorus is never exist as a single form. It is exist as a P4 form, and sulfur exists as S8 form. I want to draw the structure, then you can easily answer what's the reason behind it. So P4 and S8, let's see. Both they have a giant covalent bonding, more than one covalent bond. Look at the structure of P4 and S8. P4 is tetrahedral. Phosphorus, and a phosphorus. So it's like a tetrahedral molecule. It has less van der Waals force of attraction. Non-polar molecule. So non-polar compound, they have which intermolecular force of attraction? Van der Waals force of attraction. Now compared to S8. S8 structure, very important. S8 structure, look at that. S is like a crown-like structure. This is crown structure. Look at that. S. Sulfur. S8. But the trick is they will not give you P4 and S8. In the examination I have seen the boiling point of phosphorus is less than the sulfur. Most of the students they are going to write the answer in terms of the groups, because sulfur is in group 5 and phosphorus is in group 5 and sulfur is in group 8. Sorry, phosphorus is in group 5 and sulfur is in group 6. That's the reason. No, this is not the reason. Look at the structure. So when they ask you just phosphorus, it's P4. Sulfur is not a single sulfur, it's S8, and phosphorus is P4. Then only we can answer. Look, this is called the crown structure. It's also called puckered structure or crown structure. Look at the van der Waals force of attraction. It has 1, 2, 3, 4. It has 8. So more van der Waals force of attraction. What's the reason behind it? More van der Waals force. More van der Waals force of attraction. And carbon dioxide and SiO2, I have seen that, and P4 and S8. Okay. Sometime in 3 marks they will give you different compound and you have to predict the boiling point and the solubility and the structure. I want to do that one question before I'm going to wrap up my videos. One more question, guys. Yeah, look at that question. Some molecules are given to you, you have to predict the melting point, electrical conductivity, solubility. NaCl, let's start the NaCl. NaCl, high melting point because it has a giant ionic structure, giant ionic lattice. NaCl structure, the structure is giant ionic lattice, giant ionic lattice, high melting point and a boiling point, BP, can only conduct electricity in the molten and aqueous solution. If it is a giant lattice, no, it can't conduct the electricity. It can't conduct electricity because the ions are not free to move. Second, giant covalent, SiO2, we have done just now. Giant covalent lattice, high melting point and boiling point, not very high compared to NaCl, but we can say high melting point and a boiling point due to the presence of more van der Waals force of attraction. Reason, it has van der Waals force of attraction. Van der Waals force of attraction. Can it conduct electricity? No, it can't conduct electricity. What about Br2? Solubility, NaCl is soluble in water, soluble in any polar solvent, mostly the water. Solubility, soluble in polar solvent. It's not soluble in polar solvent. SiO2 is not soluble in polar solvent. Okay, it has no it has, first of all, it's a giant molecule and no dipole interaction, no PD, permanent dipole. So it's not a it's a non-polar solvent. It is soluble in non-polar solvent but not in the polar solvent. No Br2. Br2, what about the structure? Just a linear structure, simple covalent. It is liquid at room temperature but mostly gas, so less boiling point and less melting point. Has less boiling point, not the melting point because this is a gas. Solubility, soluble in non-polar solvent, soluble in non-polar solvent. Cyclohexane, it's soluble in cyclohexane, bromine, Br2, because of non-polar nature. Ethanol, last one, ethanol. Can bromine conduct the electricity? No. Solubility, soluble in non-polar solvent. Electrical conductivity, no. Bromine can't conduct electricity. Last one, ethanol, C2H5OH. Okay. Compared to bromine, its boiling point is high because of polar bond, high boiling point, but when you compare to the giant ionic and a giant covalent, very less, high boiling point compared to bromine. Polar molecule, due to two reasons, permanent dipole and hydrogen bonding. It is polar molecule, so it is soluble in polar solvent like water. Ethanol is soluble in water because of presence of hydrogen bonding. Okay, and it's a polar molecule. Can ethanol conduct the electricity? No. So we have touched all these. Melting point, solid has a melting point, but Br2 has no melting point. We have to consider boiling point. So it has more melting point. high boiling point because of gas, but compared to NaCl very less, SiO2 very less. Ethanol boiling point is more than the Br2. Ethanol is soluble in water because of polar nature. Ethanol has hydrogen bonding and permanent dipole. Okay, guys, please copy down that one. I want to stop my video here. We will come back in my next video. Thanks for watching. Goodbye.